All right. Thank you, everyone, for coming today for a long session about analytic data storage. This is 2.5 hours. I'm building in a break halfway through. So when we finish the first section, 10, 15 minutes, get up, walk around, take a breather, slap yourself awake, whatever it takes. Just do what you got to do. That is important. The session is really divided into a chunk on Columnstore indexes and a chunk on Parquet and Delta Lake. And then kind of the end will be how do we wrap all this together and make general best practices for all analytic data, no matter where it is stored. Because a spoiler for the whole session is that it's kind of all stored the same. And I want us to all look for that as we're doing this. There's a lot of information here. I have tons of slides, tons to say, tons to talk about. Feel free to ask questions during the session. I don't want to answer too many too early, but if you have a burning question, I'm happy to answer. Otherwise, we can save them for the end. I do have demos. I may just save them for the break in the middle or afterwards, only because there's so much to do and I don't want to fall behind and miss anything important. So with that, let's dive right in. This is me. I do a whole lot in the data platform community. I organize events up in the Northeast, like SQL Saturdays, my user group in Albany, New York. I'm from Albany, New York, by the way. And I'm an MVP in Microsoft Data Platform. I do all kinds of stuff in the data space. I write articles. I've written books. I'm just busy, but I enjoy a lot of this. It's fun to learn about new technologies, play with them, and draw conclusions about how our data is stored and how to use it. And really, architecture and design are like the thing I enjoy the most. And so really, at its core, this whole session is a database architecture session, ultimately. It's all about how do you store your data and make the best use of it most efficiently. Feel free to connect with me afterwards. That's important. If you have further questions or just want to follow me on social media, on LinkedIn or whatever, I post links to training and stuff. The agenda is kind of chunky. After a quick review of just analytic data storage and the problem we're trying to solve, we're going to talk about Columnstore, Parquet, Delta Lake, optimization features, the all best practices that are all encompassing for all analytic data anywhere. And then we'll wrap up at the end, and hopefully we're all awake at that point. And there will be a break in the middle, because I think we do want a break to kind of just take a breather from all this. So here's the problem. Wow, are people still pouring in? This is cool. Here's a general problem that we're trying to solve. And that is that analytic data and transactional data are fundamentally different. And we all know this already. I'm not telling us anything new here. But it's beneficial to point that out before we dive in. Transactional data, by its nature, lots of columns, less rows, time-sensitive, urgent, users using applications, processing orders, and things like that. That's what transactional data is all about. We're usually not taking and aggregating millions of rows. People are usually saying, give me my last 20 orders, but I want them right now, because waiting more than 2 seconds, I don't know about you, but if I go to an app and I wait more than 5 seconds, I just close the thing and they've lost my business. We're all that impatient. That's transactional data. Analytic data is kind of a different world. It can still be time sensitive, but typically we're analyzing mountains of data, less columns, way more rows, and we're not really updating as much or deleting as much. We tend to be inserting a lot more, and there might be slowly changing dimension tables and things like that. But typically, lots more data, and we have a little more control over it as engineers and architects. The data comes from transactional land, and then it makes its way over to analytic world. They're different universes, and that traveling is important. And so lots of aggregation. We have a little more control over it. When is it loaded? How is it loaded? And you might have the ability to make people be able to wait. If someone gets a daily dashboard or report or something like that, it might be get generated ahead of time. Things like you have a little more considerations, a little more flexibility. Not always, but often. An important definition here, I found that when I don't mention this in a presentation, I get asked it later. So even if you know this already, great. I just want to mention this quickly because it's an important piece of review, because it comes up a lot. Data lake, data warehouse, data lakehouse. So a data lake is essentially where you take detailed data and store it somewhere for querying for analytic purposes. Very often a data lake is when you want all of the detailed data, or you simply don't really know what it is you want yet, and so you want to keep it somewhere for reporting purposes, for posterity, for whatever. It has lots of details, lots of information. It's big, and that's kind of why it's called a lake. That's in opposition to the idea of a data warehouse, which is where you transform your data into nice, neat little business-ready facts and dimensions that people can consume. I want all the sales figures from last year, click, click, done. That's a data warehouse. And it has answers for businesses and organizations, but you've got to know the questions, you need to be able to generate that data and do a whole lot of work to get there. And the data lakehouse is the best of both worlds. You have your data lake, then you put a warehouse on top of it, and then you have your medallion structure and all those things to ensure bronze, silver, gold data, and so on and so forth. There's separate sessions out there on lakehouses and how to build them. This is not that. But I simply put this slide here just to remind us there is a difference, and that difference is important, and people always ask, what's the difference between these things? And when we talk about data storage, today we're talking about all three of these in general, not any one of them, because they're all analytic data, and we care about all of them. So to start off today, who here has used Columnstore indexes before in SQL Server or anywhere else? Wow, that is a whole lot of hands. Cool. I wasn't expecting that. Nice. So now I'm about to give you an hour's worth of review on stuff you are. No, I'm just kidding. We're not going to do that. Columnstore indexes in SQL Server are kind of cool because they allow you to store your analytic data right in SQL Server in a relational database alongside all your transactional data. It is not an open source piece of software, though Microsoft does document it really, really well. There's white papers on how they compress the data. There's DMVs that provide you insight into them. There's a lot of information you get in how your data is stored that most platforms aren't readily giving you if they're closed source, which is kind of nice. A lot of people use these because they allow you to keep analytic and transactional data near each other, or you already just have SQL Server licenses, and this is cheap and convenient. Not that we call SQL Server cheap, but it could be convenient. It's also mature now. Now in 2012, did anybody use Columnstore back when it first came out, 2012? And what did you think of it back then? I see a lot of sarcastic, I see some sarcasm and some realistic responses here, thumbs down. It was rough, and it evolved over time. Columnstore indexes, initially the technology underneath them came from SSAS, Analysis Services, which originally kind of derived itself from Power Pivot. So there's some old roots here. But with every version of SQL Server since then, it's become more and more mature, more and more featured, and now in 2022, it's pretty much a rock star feature. If you want analytic data stored in SQL Server, this is a great way to do it. And you really do get amazing performance and storage gains. When Microsoft gives you numbers, they're not making it up. They really do mean it. The gains are pretty awesome. So we're going to talk about here how data is stored in Columnstore, and it's different than what we're used to. In transactional land, you have rows of data, column 1, 2, 3, 4, all the way through, and you just keep having that. And it's that way on purpose because you don't usually go after a lot of rows in transactional land. But in the analytics world, we want columns and lots of rows. So what we do in SQL Server, first off, is in Columnstore indexes, you take your rows, however many rows you have, millions, billions, whatever, and you slice them up into row groups. And so your data is going to be stored in row groups. Each row group in SQL Server has up to 2 to the 20th rows. We'll call it a million for short. Yes, I know a million isn't 2 to the 20th, but it's easier to say. I'll probably just say 2 to the 20th so you're not pedantic with me. So within that, then, you have as many row groups as you need to store your data, and then each column is stored separately. And this is the magic of all analytic data storage, is that you don't have all your columns wedged in on pages. Each column is stored separately on its own set of pages and its own structure. Therefore, if you have a table like this that has 4 row groups and 6 columns, that's 24 segments. And if you have partitions, then it's multiply the number of partitions you have. And that's it. Each segment is kind of that unit of read. It's data for one column. And how is it stored? It's stored on 8 kilobyte pages, just like everything else in SQL Server that's not in memory. The metadata, the dictionaries, everything in Columnstore is just in 8K pages. That's it. No, nothing new and earth-shattering here, just 8 kilobyte pages, just like row store data. Now, the beauty of this, the reason why it compresses so nicely is that every segment, which means each column, is compressed separately. That's a huge deal, because each column in of itself will have a lot of repeated values and similar stuff, the same data type. That automatically will compress really, really well. Even if you don't think it'll compress well, we'll talk about compression in detail to the point where my head spins soon. And I'll show how it compresses really, really nicely. But because it's the same column, the same data type, the same similar values, so much repetition, it will compress really, really well. And that's how you go from having a table that's a terabyte down to like 50 gigs or something. And that really does happen. I've had Columnstore indexes with tens, hundreds of billions, who knows how many rows, and they can do this really nicely, which is great. So to really dive into the compression side, I want to start there. Understanding how all these Columnstore technologies work, it's really helpful to understand how do they compress data. And this gets nitty-gritty. It gets a bit into math, but I promise I won't go too deep in math. Like, arithmetic's where it's going to stop, I promise. But there's a lot of common algorithms that are used. Microsoft's compression algorithms are proprietary. They're not open source, but they document them really well. They're not afraid to talk about them. That's fine. They won't give you the source code, but that's OK. The most common algorithms that we'll talk about here are bit packing, dictionary encoding, value encoding, and bitmap encoding. And most of the information underlying these are exposed in views, which is really nice. You can actually understand and see, how does SQL Server do this? They tell you. The goals of encoding are to decrease the size of your data via lossless algorithms. This isn't like an MP3 where you lose a few hertz here and there of clarity. These are going to keep your data intact, and it's just rearranging how it's stored to make it take up less space. And then when it gets further compressed later, it'll compress even better. So that's really the goal here, is we're just shuffling around data to make it take up less space. That's encoding, and it's kind of cool. The simplest form encoding that pretty much every compression algorithm on the planet uses to some extent is bit packing. Bit packing says, hey, I have data types that have a fixed width, like an int, 4-byte int, 4-byte int, 8-byte big int, so on and so forth. But that's 32 bits. But not all the ints that I store are going to require 32 bits. Depending on the storage technology, maybe it'll shrink it down to the smallest possible size, or the least significant size of all of your data. I take the optimistic approach here. This is not how all systems store it, though. Some will simply say, OK, 950,000, how many bits does that require? And that'll become the new maximum. But the idea is that there's 288 bits here to store a bunch of ints, but you don't really need that much. You can see through the binary that you don't really need that much. Nothing here approaches 32 bits. And so if you bit pack it, you simply remove all those leading zeros, and then suddenly your data shrinks quickly. And so by taking a fixed width data type and making it variable, you immediately lop off a mountain of data. It's a very, very simple algorithm, very easy to implement, and it's used elsewhere. Row compression, page compression, it's used all over the place. This is very, very common. Nothing really extraordinary. Dictionary encoding is important for analytic data, and this is a little more involved. Essentially, what dictionary encoding says is we have repeated values. They're kind of chunky, and I need a way to simplify and make them be less chunky. And if they're repetitive, the answer is make a hash table. And so we'll say, here's a table. It has some strings in it. The strings take up anywhere between 0 and, 1,000 bytes. OK, great. Let's make a hash table, put every unique value in the hash table, and then replace those values with lookups. And so now my table, instead of having all these chunky strings, has little numeric pointers that go over to the dictionary that tell you which row to go to. And so the bigger your data is, the more you gain from this. The more repetitive your data is, the more you benefit from it. And in Columnstore indexes, it can do this on many data types, not just strings. It can do it on decimals, can do it on big ints, can really do it on anything. And this is all automatic. One thing I didn't mention yet is that all the compression in Columnstore is automatic. SQL Server simply decides automatically what to use, what it thinks will have the biggest benefit, and it goes from there. You don't control it, really. Yes?
Yeah, quick question. So, not Columnstore, I know Vertipack, dictionary encoding is mandatory, right? Is this smart enough that if you, say, have a mostly unique column, that it's not going to try and dictionary encode? Because you wouldn't get a benefit, it'd be worse.
Generally speaking, it will. So the question was, will a dictionary encode intelligently? Will it make the right choice and choose to not do it? And the answer is usually. It's not perfect, but it will try very hard. If the column is very unique, it will not use dictionary encoding. If it repeats a lot, it will. But if your columns are very, very wide, you can actually run into some issues, which I'll get to in about 20 seconds. So dictionaries, and this is a problem in all Columnstore technologies, are not infinite. Nothing's infinite, right? Does anybody have infinite anything in life? Happiness, love, I don't know. There's some things you could talk about perhaps, but dictionaries have a maximum size in SQL Server of 16 megabytes. And that's usually more than enough. But if you have a column that is very wide, it is possible that as you add more values and more things are added to the dictionary, it could fill up. And what happens when it fills up? Your row group will stop growing, and it'll make a new row group with a new dictionary, because you can only have one primary dictionary per row group. And so as a result, in theory, if you have very, very wide columns and it chooses dictionary encoding, you could get in trouble. And very often in those cases, normalization is a nice solution. We can talk about that a little later. I point out the 16 megabyte rule here only as an aside. Most people will not be affected by this. It's only something you should look into if you run into problems. Like all things in life, don't optimize before you have a problem unless you know how to architect or whatever. You don't fix a problem you don't have, basically. So here's an example. Let's say you're running a bakery, and like most bakeries, you may have a few dozen things that you sell, and of them, you have your most popular items, your least popular items, but a bakery doesn't sell an infinite number of things. They might sell 10 or 20 or 50. So here's a little subset of data from a bakery, and they're just strings, and I have the number of bytes that are in each string, as well as the name of the string. This is assuming varchar. Obviously, if you're in n-varchar land, it'll be double the size in bytes. And we have 203 bytes here. And some things repeat here, because bakeries have favorites, right? If you're a bakery, you probably have your special of the day, the cheesecake everyone loves, I don't know, whatever, the double chocolate brownie. So the first step for dictionary encoding is to build a dictionary. That was kind of obvious. So there's a dictionary. It turns out there's only 5 unique values here. 0, 1, 2, 3, 4. That's it. And this is very common. Most restaurants will have potentially a big menu, but things repeat a lot, and certain things get ordered a whole lot. So we can see the dictionary is 82 bytes. The byte size of one of each value is 82 bytes. We can see that here. And the index IDs are small. They're no bigger than 3 bits, 1, 0, 0. That's it for 4. So that's relatively small. So now we have a dictionary. We've built it. And this is kind of how SQL Server does it, by the way. It's a little more technical, but this is basically what it does. And then it says, all right, now we don't have to store all those values anymore. We can just store the index IDs instead. And so we do that. And now we have an 82-byte dictionary. We have a 20-bit encoded data pile. And this got a whole lot smaller. So it's very easy to take a dictionary, and this is just for 12 values here or something like that. If you have hundreds, thousands, millions of values, you have a whole row group with 2 to the 20th rows, and values, there's only a handful of unique values, you get a lot of savings. From my experience, when you have a string in a data warehouse or a data lake, typically for most non-description-y columns, the average unique values are between 200 and 300, just on average. It's a rough average I've seen through just data profiles over the years, which means you have 1 million rows and 250 values. That's a lot of repetition. You can divide that out. And so we save a whole bunch of space here. We can see that we save around 115, 120 bytes, which is over 50%. So huge, huge savings through compression. And the more repetitive the data, the bigger it is, the better the savings. The next one involves a little math, and this is also exposed in SQL Server. They do tell you how it works. Value encoding is kind of cool. Basically, you take your data and transform it to make it smaller. And initially, when I first saw this in my life, I was confused, and I had to think about it a lot before it made sense. And I'm hoping that what I'm showing here makes sense of this so it isn't awkward. But the real basic idea is to transform your values to take up less space. And that's the whole point of all encoding and compression, is make it take up less space. And this can be combined with dictionary encoding. So you could have dictionary encoding create lookup values that are then further compressed through encoding. It's totally 100% fine. The dictionaries can be further compressed. SQL Server can compress a lot. So here's what this looks like. I'm going to give you a couple of examples here. I think 3 at least, or 4. So imagine you have those values over on the left here. And those values are big numbers, and they just happen to all be divisible by 10. So I can store them the way they're stored right now. They're integers, and I can bit pack them to make them smaller, but they still require a bunch of bits. But in theory, I could just say, hey, pick a common divisor, the biggest one that'll squeeze into all of them. This is like math class in middle school. And divide them all by 10. So now all the numbers shrink. They go from 65,000 to 6,500, from 100 to 10, from 30 to 3. And then the size in bits goes down. And so now all I have to do is store the new value, and then in the metadata for the encoding, just mention that there is a multiplier of 10 to the negative first, and we're done. This saves 25%, just like that. And so all it is doing is dividing or multiplying by a number. It's multiplying, actually, not dividing. Division is just multiplication by a negative, right? Anyway, that's one example of how to do it. You can also do it through subtraction or addition. Same exact idea here. I took the same data set for fun, and I said, all right, the smallest number is 30. What if I just subtract 30 from all the numbers? So 30 becomes 0, and all the rest get reduced by 30. If I do that, well, SQL Server wouldn't do this. It would know better. I only saved 5 bits, and that's not very impressive. So it wouldn't do this, but I show this here as an example of how it would look. If I subtract 30, I would store all the new values, and then negative 30 as that base. So we wouldn't do this. Didn't save enough. Here's an example, though, that I never really occurred to me until I saw it in implementation years ago and was surprised. In theory, you think of identity values and say, well, identities are all different, right? They're all unique values. It's an identity. It's a PK or something, right? Therefore, you can't compress it. But that's not true. You can compress it really beautifully using the same algorithm. I hear of identities going up from 1.5 billion. That takes up a lot of space, right? Those are 32 bits, pushing big int size soon. But I could just subtract 1.5 billion from each one of these values. And when I do it, I go from humongous numbers to little numbers that take up almost no space. So I go from 320 bits down to 26. And so if you ever thought to yourself that identity columns can't really be compressed easily, they can. And value encoding shrinks them down to nothing, just like this. You can save an mountain of space. So don't ever think that your identities won't shrink nicely in Columnstore. They will shrink beautifully. Here's another one, and this is an important downstream operator. So far, value encoding, dictionary encoding, and bit packing shrank down our data a whole bunch. So we've shrunk our data, we have re-represented how it looks, we've made it smaller and a little more complicated, but a lot smaller. Now we're going to say, all right, here's the part with repeated values that we care about. We want to summarize repeated values and not repeat them anymore. This is the fundamentals of compression, right? We take repeated values and we summarize them so we don't repeat the same things over and over and over. This is very effective on sorted data, which we'll talk about soon. But you can see here I have a raw data set on one side, and then I simply say on the other side, take each value, tell me how many times it repeated, and then we're done. And that's our run length encoded data in a simple level. And the size goes down. Now you'll note that in this case here, I didn't save much. I only saved a few bits. And so I didn't really do much here. I showed how run length encoding works, but my data is not sorted, and so I still have repeated values. Because SQL Server can't automatically reorder the data, can it? Or can it? We'll come back to that in a moment. So just kind of an FYI here about column store compression and how it works. There's 2 algorithms that SQL Server uses for column store compression. One is called xvelocity, and that's for column store. It's the proprietary algorithm. And one is called express, which is for column store archive. I'll talk about archive a bit more later. It's essentially a more aggressive compression algorithm. Takes more resources, but it makes your data more shrunk. So if you want smaller data, you can use it for that, but it's going to be a little more expensive to read and write. Both of them will always use least bit packing and run length encoding, and then situationally will apply other algorithms as needed, depending on your data. To the point from earlier about dictionary encoding, will it always use dictionary encoding? No. It'll use it when it sees a meaningful savings, and it's very rare that it'll make a mistake. I've seen it make mistakes, but it's rare enough that you're not going to budget for that or think about it or worry about it because it's very rare. And it's getting rarer with time as this gets more and more mature. And these are closed source proprietary algorithms. You can't see the code, but they tell us a lot about how it works, which is very nice. Thank you, Microsoft, for telling us useful information. I mentioned just moments ago that how do we fix run length encoding if your data is not ordered? Like I had a bunch of repeated values that I couldn't compress. It was useless. I saved 2 bits. Nobody would ever pay for that. That was terrible. But we can fix that. So this was added to Columnstore fairly early on. It's called VertiPack optimization. And you've probably heard the word VertiPack before in other places, right? That word's appeared in your lexicon, VertiPack storage, VertiPack engine. It gets reused over and over and over to the point where, boy, we've heard it a lot. VertiPack optimization ultimately comes from the idea that within every row group, order doesn't matter. This is a very important fundamental for Columnstore indexes, is that Unlike row store data, where you have a clustered index with a PK and it automatically orders your data, like I have a mountain of data ordered from 1 to 1,000,000, and if I insert a brand new row, it's going to say, hey, I've got to shove that right into the middle of my data in the right place. In Columnstore world, it doesn't actually matter. Within each row group, the order of data doesn't matter, because that row group is a unit of data. It's going to be read segment by segment, and it's its own discrete unit of work. Therefore, VertiPack optimization will simply say, after we've encoded everything, but before we do the run length encoding, we can reorder the rows in each row group. There's no reason not to. It doesn't make a difference. And so it will automatically calculate what the optimal way is to order them to make the data compress the best. And the goal is to make it so that similar values in all the columns group together to save the most storage possible. Is it perfect? No. But it's very, very good. It will quickly identify which columns are the most inefficiently stored, would benefit the most because they have the most repetitive values, and then reorder to group them together. And this is not a cheap process, but it's important, and it will really improve compression ratios. If you compare data that's been VertiPack optimized versus data that is not, you will see a difference, and the difference can be 25, 30, 40% for some data. It's huge. So when we talk VertiPack optimization, we're talking about reordering data in row groups so it can compress better. So I'm going to start with this example here. You can see on the left is the data I just had a few moments ago, and it barely repeats. I have a few things that repeat, but it mostly doesn't really repeat in order. But let's say I were to reorder the data. This is one row group, and I reorder it all, and I put it in order from 0 to 4. Notice the data size didn't change. The purpose of VertiPack optimization is not to save space. It is to make the data easier to compress later. That's all it does. It will never save space in of itself, but further down the line, space will be saved when compression occurs. And so it's 20 bits on the left, 20 bits on the right, but instead of it being 0, 1, 2, 3, 4, it's 0, 0, 0, 1, 2, 2, 2, 2, and so on and so forth. If you have 1,000,000 rows, you'll get a lot more of this. And that's good. And this leads me to the idea of data order. This is a fundamental concept in all of analytic data storage, and that is that the order of your data will influence how well it compresses, and you have control over that. You have a lot of control over that, and in fact, most engines don't have as much control over it as you think. VertiPack optimization is cool, but it's only helping you within a row group. If you have 1,000,000 row groups, you have a giant Columnstore index, the order of the data in that index is fundamentally going to be the order that you insert it. So if you insert data into the Columnstore index every single day, it's going to keep just putting new data on top forever. And that's your data order. If I insert a row here and then a row over there, the row's over here and over there. It's not going to reorder it for you outside of the row groups. And what this means is that when you insert data into a Columnstore index, or really any analytic data storage, you want to insert it in some fundamental order. Now, the order is usually going to be a time dimension. Most analytics occur based on time: weekly, daily, monthly, quarterly, stuff like that. And so whatever your most fundamental predicate is, the most fundamental search criteria, grouping criteria, whatever, that becomes your data order. So you're incentivized now to say, OK, we're going to load data every day, and we're going to do everything we can to keep the data in order. Otherwise, you've got to rebuild everything, which takes a very long time, and we don't want to do that. But more than that, when data is ordered by some fundamental dimension, it will compress better for two reasons. One, you have the benefits of run length encoding and things like that. It will say, oh, here's all the data for November 8th. OK, you can compress November 8th into oblivion. But data in close proximity to other data by time is going to be more similar. And we can demonstrate that very easily. If you had a sales order system or a processing system or any analytic data pile, and you said, hey, take data from today and compare it to data from yesterday. How similar is it? And then take data from today and compare it to data from 10 years ago, you can be guaranteed, without question, the data from today and yesterday are more similar than data from today and 10 years ago. Why? Because the customers change, the employees change, the sales processes change, your software has changed, you've added new features, et cetera, et cetera. And so as time goes on, things will look different. And that's just the nature of data. Therefore, you want to keep your data ordered. And we'll talk about that a bit more later. But if order is ever disrupted heavily, you should fix it. In the Columnstore world, fixing it is a nuisance. We'll talk about ordered Columnstore later. It's not quite as awesome as it sounds, but it is kind of cool. But in your world, if you're starting out and you don't have access to that or you don't want to use it, then you have to take a clustered row store index, throw it on, wait, and then swap it out for Columnstore, and then it's magically happy. If you're using non-clustered Columnstore, then you're at the behest of the underlying data. So whatever your underlying data order is in transactional world is, you inherit it, and it's whatever it is. But there is an upside here. There's a silver lining. If you have older data that has been written and is done data, how many people here have data in their world that is done? Like you've written it, and now it's going to sit there forever minus the rare maintenance or release. And there's lots of hands here. Guess what? Once you've ordered and compressed and stored your done data, it's done. If you have it in separate partitions, it can just sit there happily for the end of time, nicely compressed and perfect, and you can just leave it alone. And that is a great, advocate for partitioning in this world. If you have giant tables you want to partition, Columnstore is even more so, because analytic data by its nature tends to be created, we muck with it a bunch, and then at some point it becomes either stale or mostly stale. And by stale, I just mean we don't touch it anymore, we don't play with it, we just read it occasionally. And once you've done that, it doesn't need to be in a structure that encourages modifications anymore. So you can make it perfect, compress it, leave it done. Are there any questions, by the way, before I continue to plow forward? Or are we doing great so far? I don't see anybody napping yet, so that's good. Though if you are, I won't take it personally. Just don't snore. Please don't snore. Snoring's rude. Thanks. Now that we've introduced data order, we have the benefit of what data order does for us, because it does more for us. So Columnstore indexes by its nature can have millions, billions of segments easily. If you have an index with 1 billion rows in it, that's kind of like 1,000,000 times 1,000. It's 1,000 row groups. And within each row group, you have a segment per column. So you can have thousands and thousands, tens, hundreds of thousands of segments easily. But because each segment is stored separately per column, we don't have to read it all. This is not like transactional world where I have to read pages full of all the columns I don't give a darn about. I don't need that. So here's what happens in analytic world. I say, hey, go to my Columnstore index and give me columns A and B only. I don't want the rest. It won't read the rest because they're stored separately in their own segments. And so if I were to do this example here, I have 6 columns. I can say I just want columns A and B. Then I get back columns A and B, but I don't read all the segments from D to F. I don't need to. They're stored separately. My metadata tells me exactly where it is, and so I just leave them alone, and they can sit there and not get read into memory, which is good. It means you can have a Columnstore index with a lot of columns, and that won't kill your performance. We always in transactional world say, oh, that table has 100 columns. How does it even perform? Do you want too many columns in Columnstore? No, nobody wants too many columns. But they're stored separately, so you're not going to pay a price for it immediately, aside from all the storage it costs. So the moniker we always say about don't select star or only select the columns you need, it's as valuable as ever here because it won't even read the data. And that's beautiful. That's kind of the vertical slice by column. But we also horizontal slice the data too. And this is even more awesome. Now, this is where ordered data is necessary. So imagine underneath this data, it's ordered by date. The beginning of the data is January 1st, 2024, and the end of the data is today, November 2024. Do I know what date is today? It's fuzzy. But anyway, it's ordered by date. And so let's say I were to go in and say, hey, give me a few columns out of this table where the date is January 5th. SQL Server will go and check the metadata and say, hey, these row groups don't have any values that match that predicate. I'm going to ignore them. And so by querying for a small range, and I've ordered data, just like how I ignored the columns I didn't need, it's going to also ignore the rows I don't need. So in this example here, if I only needed data from a single row group, because the filter criteria can be eliminating all the rest of it, I'll just read the one row group. This requires ordered data, though. If your data is not ordered, this won't work. But it doesn't need to actually be ordered. As long as the same values are in the same place, it works out nicely. But ordering is the easiest way to accomplish that. The next question you're going to ask is what happens when I combine these forces together? And the answer is this is where you get a lot of your performance gains in the reads, is this right here. So we eliminate columns we're not reading. We eliminate row groups for predicate components we don't need. And then we're down from 24 to 2, or 24,000 to 2,000, or 1,000, or 10. And so segment elimination is how filter predicates and not querying all your columns allow you to ultimately not have to read a lot of segments. So you can have a Columnstore index that has millions and millions and millions of segments, but you only read 10 of them, or 100 of them, or 1,000 of them. And that's why they can be so fast, because under the covers, it automatically just does this for you, no matter what it looks like. And that's really, really nice. And if you have statistics IO on, if you use that, it will actually tell you about the segment elimination details, how many were read, how many were skipped. And that's really useful. If it says that you read 100 and skipped 0, you got no segment elimination. If you read 10 and skipped 100, that's great. If you read 1 and skipped 1,000,000, that's even better. It'll never be that perfect, but this will definitely improve your query speed because you're not reading data you don't have to read. Now this is all about, I'm going to stop actually for 1 second here. Any questions about how we read data quickly from Columnstore before I jump into writing data quickly to Columnstore? Yes?
When it's storing compression for each of the column store, does it use different algorithms for each of those compression algorithms?
Great question. The question was, will different segments be stored with different compression algorithms? And the answer is yes, because each segment is stored individually for a different data type, a different column. Each segment can be compressed differently based on the contents of not just the column, but that one segment's worth of the column. So it is possible that the same column will have segments compressed in different ways. And different columns in a row group will be compressed different ways, which is good. That ensures that you're compressing the most optimal way possible, because you're only ever looking at 2 to the 20th values for one column. Excellent question. Excellent, excellent question. Now, in the same way that we have all these optimizations to make reading from Columnstore fast, we've got to also be able to write to Columnstore fast. Now, remember that anything like a Columnstore index, no matter where it's stored, is a heavily compressed pile of data. Decompressing it is expensive. Compressing it is expensive. Mucking with it and changing it is expensive. Just remember that for the remainder of this presentation, that mucking with compressed data is expensive, and it's always expensive. And therefore, we don't want to do it unless we have to. And doing it too often is really, really expensive. And we can demonstrate that very easily and break a server by trying hard to force to do things that it doesn't really want to do. So here's what happens. There's 2 ways for data to get inserted into Columnstore. It can go in a bulk insert, which is really, really nice. If you insert in one transaction 102,400 rows, it's very specific, or more, then SQL Server will do it via a bulk insert process. In other words, it's minimally logged. And so enough information will be logged to allow your transaction to either be completed or roll back, but it won't log every single itty-bitty detail. Because I'm sure you all know from the transactional world, if I have a row store index and I insert 500 million rows into my clustered index, my normal row store clustered index at one time, what happens to all the users trying to access that data? What happens? They get locked, they get blocked, they wait forever, and on top of that, the transaction log goes like this, right? Because you've got to log that entire transaction in one operation. So your LDF gets giant, your transaction log backup takes forever. So downstream, it's like you swallow a cantaloupe and you're watching your body digest it slowly in one piece. Yeah, imagine that. That's what it's like pretty much. And in Columnstore, though, this is analytic data. The idea of inserting lots of data at once is very normal, right? Because we have data loads, and we may insert millions of rows at once. I have an API I monitor. The API does 100 million transactions a day, and I want to save the details of those transactions somebody or for querying later. Well, that's a lot of data. I'm not going to do it 1 row at a time. I'm not going to batch it 1,000 rows at a time. I want to say insert 1 million rows at a time. Go. And by doing the minimally logged bulk insert, it's faster. Therefore, you want to take advantage of that. So in Columnstore, you want to insert lots of rows at once, not onesie twosies. You don't want to batch it 1,000 at a time. You won't get anything. But If you insert less than 102,400 rows, it goes to what's called the delta store. And this is essentially a B-tree structure. It's compressed, that stores the data kind of in a more classic structure. And this is not a bad thing, by the way. I make it sound bad, it's like a heap, but it's actually good, because if I trickle insert data into Columnstore, I don't want it decompressing the Columnstore segments and then adding data and then recompressing them over and over and over and over. Imagine if I inserted 1,000 rows and each row went to a different row group. Would I really want to have to decompress millions of segments and then recompress them all at the same time? No. You'll be waiting forever. So instead, it will put the rows into the delta store, and then asynchronously in the background, SQL Server will push that data in on its own time. And this is good. This is helping you out. It's ensuring that if you trickle insert rows, it will collect them in one place and push them through at the end. This is ideal. So if you insert a little data, it gets accumulated and inserted. If you insert a lot of data, you get minimally logged, super speedy bulk insert. That's ideal. This all works because of metadata. Everything I've talked about so far, segment elimination and all this fast reading and writing, the key to all of this is metadata. So statistics are stored in tables in SQL Server. Are statistics always accurate? Are they? No. Oh, they aren't. Why not? Well, you can't keep them updated all the time. It'll take too much effort. And so in classic tables where you have stats, the stats fall out of date, and you just hope they're close enough that you get a decent execution plan and your life isn't made miserable at 2 in the morning on a Sunday, right? Metadata in Columnstore indexes is 100% accurate. So when segments get compressed, when row groups get created, metadata is written about the row groups and about the segments, and that metadata is precise. It's exact. It is not an estimate. It is not to get updated. It is perfect. It includes things that are very useful, like the number of rows, how big is the data per segment, how are they nullable, mins, max. The mins and maxes are key, by the way, for segment elimination. If I have a date column and it's all perfectly ordered, and I query by date, and I say, give me all the data for the first quarter of this year, and my data is perfectly ordered by date, it can automatically see the mins and maxes in that segment across all the row groups and ignore the ones that don't match. So this is important. Data order is critical to that, and the metadata is what facilitates it. And I put a few examples of dynamic management views here. There's some other ones as well if you want really nitty-gritty about the physical storage of this stuff. But the DMVs are great because they tell you exactly how your Columnstore data is stored. So if you're curious, you can look and say, I want to know how many row groups I have. How big are they? How many rows? What are the mins and maxes? That'll also tell you if your data is nicely ordered or not, too. You can check and see, is it compressed well? It'll even tell you, was VertiPack optimization used for a row group or not? Because there's scenarios where it won't be, potentially. And so this metadata is exact, and it's useful, and you can query it and get information about it, which is really nice. I mentioned this before. I'm going to mention it just one more time really quick. If you've done BCP before or Open Row Set or things like that, you've taken advantage of bulk insert in other processes. Like I want to pull in data from a CSV file into SQL Server. You can do a bulk insert and benefit from minimally logged stuff. This requires no special operation. If you're inserting data into a Columnstore index and you insert enough rows, it will try to do a minimally logged insert automatically. You don't have to tell it to do anything. You don't have to say bulk insert. It will simply do it. And as a benefit, if you have parallelism enabled, it can do parallel streams to insert data. If I insert like 1 million rows at once, it can say, I'm going to do it in 2 threads at one time to make it faster. And so it can do a lot of cool things to make it even faster. This is automatic. It's nice. I like automatic. So here's a bigger picture now. I talked about how we insert data into Columnstore, how it can be either bulk inserted or trickle inserted into the delta or row groups. What about deleting? When I go into Columnstore and I delete a row, is it going to decompress the whole thing, delete one row and recompress it? No, that's a lot of work. I don't want to do a lot of work, and neither does SQL Server. It wants to be lazy too. And by lazy, I mean you use less compute. So what happens is when you delete rows, it will create delta row groups. Delete bitmaps, not delta row groups, sorry. Delete bitmaps. A delete bitmap is simply a bitmap. It's ones and zeros that point to rows in the row group and say, yes, it's deleted. And that's it. That's all it is. It's a soft delete. So if I have a row group that has 1 million rows and I delete 10 rows, a delete bitmap will be created over that row group, and it'll have 10 ones that point to the rows that are deleted. Now, when I go ahead and I read my data, it will check to see is there a delete bitmap, and if there is, it will simply omit those rows, because that's the fastest way to do things. It's expensive to decompress and recompress, but having a soft delete is really fast. And we do that, right? Like, how many systems have we built over the years? We have a column called is deleted or is archived, right? I didn't do that for fun. There was a reason for that, either for efficiency or for posterity or for some reason. It's no different here. Do the deleted rows get cleaned up? Potentially. We'll talk about that later. But basically, this is a soft delete. So just know that when you delete stuff in the delete bitmap, these rows are soft deleted. If the data is in the Delta store and you delete rows that are there, they actually get deleted, because that's just a B tree and it can go in and delete it. So that's automatic, but if it's in the compressed row groups, it's soft deleted. And you'll have records of that. And you can inspect all these structures in storage if you want to, if you're so inclined. So when we read Columnstore data, we will take the contents of the compressed row groups and add on the contents of the Delta store, if it even exists. If you don't have anything in the Delta store, they won't exist. But if they do, and you probably will, because let's say you insert 1,100,000, let's make up a number that's amazing, 1,005,000 rows. The first 2 to the 20th rows will get inserted into a row group automatically, bulk insert, and the remainder will go in the Delta store. And so you're going to have Delta store. You can't help it. It's part of life, and that's OK. And then we subtract whatever is in the delete bitmap, and then that goes away. So you're going to read multiple structures, but this is ideal. This is what we want. We want to have these structures here. They allow you to read and write data faster. The goal is to not decompress and recompress data more than we have to. But there's a challenge here. What happens when you issue an update statement against a Columnstore index? Is it pretty, or is it not so pretty? And the answer is you get an asterisk of pain. When you update, you have the challenge of, I need to do this in one transaction. I need to do an insert, because an update is an insert and a delete, right? I delete data and insert it, but it's not a delete and insert, because I've got to do it in one transaction. So what's really going to happen is it's going to start locking stuff. It's going to put stuff in delete bitmap, and then it's also going to have to insert in the Delta store. It can't do a minimally logged bulk insert as part of this. If I update 1 million rows, the insert portion will not be minimally logged. It'll be full. You can test this. You can do delete 1 million rows, insert 1 million rows into Columnstore as a test here, and then over here do the exact same thing, update 1 million rows. So you get the same results. And your transaction log on the update 1 million rows will be like this, whereas on the insert and delete, it'll be like this, tiny comparatively. So updates do not benefit from a lot of the optimizations that you get by inserting or deleting. And so I put an asterisk here. If you're migrating workloads over to Columnstore from elsewhere, beware of updates. If you update like thousands of row groups at one time, I promise you your server is going to cry a little bit, because it's not going to use any of the technical benefits of Columnstore to do it. It's just going to be slow and painful. So beware. Updates have asterisks, and they're painful. They're not pretty. Starting in 2019, we began getting some cool benefits. I mentioned data was soft deleted, and that soft deleted data was cool, but it accumulates, right? And why do you need to keep them anymore? We don't have time travel in Columnstore like in Delta Lake, and so we can get rid of them. And so the idea of merge and self-merge were added to SQL Server to Columnstore. Merge and self-merge are operations that occur. You can make them occur using index reorgs. And what they essentially will do is combine undersized row groups, because the less row groups you have, the better. And they will then also get rid of your deleted rows. So in this hypothetical example up here, I have some smaller row groups that can be combined and still be under 2 to the 20th rows. They get combined. I also have deleted rows, and they'll get removed. So it'll actually go ahead and do the work of decompress the row group, remove the deleted rows, recompress it, and then jettison the delete bitmap, because we don't need it anymore. And the benefit of this is you shrink down your data, because as we know, soft deleted data takes up lots of space. but real deleted data does not. So operations like this allow us to go from all the rows on the left, however many that is, 3 point something million rows, down to a whole lot less. And so by using reorgs, you can clean it up. And the older versions of Columnstore couldn't do this. You had to do rebuilds or do other things to get rid of this data, but now it can happen much more easily. And so these are optimizations so that you don't have to go through and do manual work to clean up old data. It'll just do it automatically. And undersized row groups are a problem because your minimum read is a segment. And if I have to read 2 segments to get data, that's not going to be as fast as reading 1 segment. Even if the 2 segments combined are the same size, it takes work. I mentioned archive compression earlier. Archive compression is basically Columnstore compression on steroids. It's more effective, you get a better compression ratio. In general, I've seen it benefit 15, 20, maybe even 25%. You can get more. But it requires more computing resources to compress it and decompress it. Therefore, you don't just use it. You want to use it on colder data, less warm data, older data. You can do it on a per partition basis, though, which is nice. So I can say, hey, I have a giant table, and I have it partitioned by year. My data from before last year, I can just archive compress. Give it the most aggressive compression possible because we don't read it much, and we're not going to write it again. And then our new data that we're still writing to, we'll regular column store it because that's fine. You can make that choice. Just like kind of how you can partition by partition decide between no compression, row compression, page compression. It's the same in Columnstore world. Are there any questions here so far on reading and writing Columnstore indexes and all the optimizations and benefits along the way that we, yes, up here. This is going to sound silly, but there actually is a very easy solution to updates, and that is rewrite your update as an insert and a delete. Yep, and it sounds really silly, like, oh, just replace it with delete, but actually it works out nicely because your delete will do a nice, fast, soft delete, and your insert, if it's big enough, will bulk insert and not go in the delta store if it's enough rows. But doing it in one operation is much faster than doing an update. So easy optimization, easy fix. I see a lot of hands. We'll start over here.
Is like fragmentation measured the same way? So like OLS maintenance scripts would pick that out to know what reorg those?
It's an interesting question about how do you measure fragmentation in Columnstore world? And the answer is it's completely different. OLS scripts aren't going to really give you a meaningful number here. So what you're looking for, really the only, in older versions of SQL Server, things could get fragmented more. In newer versions, if you just do like a lot of people just do a daily reorg after they load their data for simplicity just as a habit. But basically, the only real true way that a Columnstore index gets fragmented is if your data gets out of order. Because when your data gets out of order, you start benefiting less and less from segment elimination. And that's really the only way you truly can get messed up over time. If your deleted rows get removed via a reorg process, self-merge, or undersized row groups get combined, all those problems go away. Now, older versions of Columnstore didn't have those features. We're back in 2016, 2014, even 2012. You're back in the Stone Age, and you're missing features. If you're in 2019 or 2022, you're getting all the new and awesome stuff, which helps a lot here. But a lot of that's done through reorgs. Yes, in the back.
Yeah, are there unique Columnstore indexes? And if so, is that causing complexities with having to decompress?
I couldn't hear you, sorry, what was that? So the question was, are there unique Columnstore indexes? And the answer is no. This is not like a row store index. You can't say create unique Columnstore index or whatever. You can combine clustered Columnstore and non-clustereds, and that can include unique non-clustereds. And you can combine non-clustered Columnstore with clustered. Just be aware that when you mix those technologies together, there's going to be compromises. If you have a clustered row store and a non-clustered column store, that non-clustered column store is going to inherit the row order from underneath it. It can't control it. And so if the row order is nice for compression, great. If not, it's going to be kind of rough. Similarly, if you have a clustered column store and you put row stores on top of it, those row stores won't compress as nicely as the column store. You can very easily say, like, hey, I have a column store indexed to 100 gigs. If you were to put a couple of row store indexes on top of it, it can get really, really big. And now you've got to check uniqueness on top of it. So you can take a unique index and put it on top of column store. But you're going to see your space balloon. In general, I encourage people to use validation processes to maintain those constraints as much as possible, and only put non-clusters if you need them, because they will be expensive. But good question. I saw one. There we go. So the question is, how do you handle a slowly changing dimension table in Columnstore? And the answer is you don't want to do updates. You want to replace it with deletes and inserts. But I would also ask, is this table ideal for Columnstore? Does the data ever get done, or is it always getting changed? And what I might consider, if your slowly changing dimension table really is monstrously big, like billions and tens and hundreds of billions of rows, maybe consider having two different tables. For the data that's done, that's older versions, put it in the Columnstore index, and then the newer data that's still being written, put it over here, and then just kind of union them together. I know it sounds a little sloppy, but a slowly changing dimension table is kind of the best and worst of both worlds in terms of reporting. You have lots of things that are changing, but then you have your old data that doesn't really change very much. But that's a great question. One more question from back here before we continue.
Is there any kind of read optimization if every single row and row group is in the delete bitmap? Like, can it just skip that, or does it read it in and then throw it away?
The question is, if you have a row group where it's mostly deleted or all deleted, what happens? And the answer is SQL Server needs to combine everything together. It's going to read the data. So if you have a row group that's all deleted, it will still read that row group, and then it will throw it away, which sounds kind of lame, but at the same time, when you do a reorg next time, it'll go poof. And so my general advice is just do a reorg once a day after you load data, or just in some off-peak time whenever. A reorg is not blocking, it's not offline, it won't break anything, and it will take care of all your deleted rows, it'll take care of your undersized row groups, it'll do all that beauty for you. I have a little more here before we take a break. I do think a break is a good idea. I think 2.5 hours straight. Does that sound fun? 2.5 hours of this? Woo! All right. I might be energetic, but we wouldn't be if we kept doing that. There's a feature added in 2022 called ordered column store indexes. This is situational. It sounds really good. It can be really good, but it's limited. It only works for clustered column store, though the documentation mentions non-clustered order. I don't really know why. I think it was a bug. I mentioned it to Randolph West, and he immediately went to the team and was like, oh, I'll take care of that immediately. So maybe that was a leak. I don't know. But ordered column store is for clustered only. It allows you, when you create it, to give it an order based on a column. And what that will do is say, and this is 2022 only, it will say, I will take any data you insert and pre-order it by those columns. And if I do a rebuild, I can order it by those columns. There are downsides, though. One, it's sorted in tempDB. So wherever your tempDB is, you're going to get kicked in the face. And it's an offline operation for whatever row groups you're dealing with. So beware that if you use this feature, it's kind of cool. It will not reorder your existing data, though, unless you do a rebuild. So if you have 100 billion rows in a column store index and I insert 1 million rows, it's not going to reorder the 100 billion rows. If those 100 billion rows aren't in order already, sorry. But the new data being inserted will be kept in order. So if you inserted 10 million rows, those 10 million will get broken up into row groups, and they'll be in order by whatever columns you specify. So it's a useful feature. Just beware that it doesn't solve every problem with data order. You're still kind of responsible for data order. It just helps you a bit, so you don't have to sit here and like insert this date, and then this date, and then this date, and then this date. It'll help you a bit. Just beware that it's an offline operation. So if you were to do this in the middle of a high traffic analytics time, you might block people and make them sad. So just beware. Cool feature. I'm sure it'll be more mature in the future. It's not 100% mature yet, though. So just have a little caution with it, but it is kind of cool. And I was glad to see they built this, and I'm sure the next version of it will be better. All right. It's been an hour. I'd love to take a break. If you're interested in chatting during the break, we'll do about 15 minutes. So right now it is about 3 o'clock. So at about 3:15 we'll start again. So kind of make your way back around 3:10, and right at 3:15 I intend on blasting off and continuing. So take 15 minutes, use facilities, get a drink, slap yourself in the face, whatever it takes, and we'll continue then. We're back from our 15-minute break. I hope we're all refreshed. We're awake now. We feel better. We splashed water all over our face. What's in those cans?
Hopefully smarter than water, we'll see.
Woo! All right, awesome. This is going to be a great session. I can't wait. So we talked all about Columnstore indexes, and they are cool. And they're native and SQL Server. They reside next to your transactional data. They can do so many great things for us. But not all of our data is stored in a relational database. We store data elsewhere, like in Fabric or Synapse or in Databricks or about 1 trillion more places that won't have a relational database. And that's OK. And so what we have now is another way to store data, and these is in files. This is the opposite of a database, right? We had a database over here, nice and clean, and if you're a database administrator, engineer, this is like perfectly made sense to you. If you're not a database administrator, this makes sense to you. And so now we're talking about files. Off into file land. The Apache Parquet file format is an open format. That's one of the biggest benefits and why it's become so popular. Because it's open, it's portable. No vendor lock-in. If I take and I create Parquet files here, I can lift them up and bring them anywhere else I want and keep using them. And that's really nice. If you have them in one place in Azure, you want to move them somewhere else, you can. If they're not in Azure, you want to put them in Azure, you can put them in Azure. If you want to take them out of Azure and put them somewhere else, why would anybody do that? You could. And they're open, so you can do that. Just like Columnstore indexes. And again, how many people here are like more database-centric in general? I'm just curious. OK. I built this presentation with that assumption, and I'm glad that was a good assumption. Whew. So it's very, very similar. Parquet file format is column-based storage. It's going to sound like deja vu for the rest of the presentation, and that's intentional. We're here until about 4:30, so hopefully we're all ready for this. But you're going to have deja vu, and that's good, because that means that we're not learning an all-new thing here. It's new-ish, but the key to Parquet is that this is way better than storing data in classic data formats. If you store data in CSVs and XML files and JSON files and stuff like that, you know the pain. You know what a CSV file is like. Who here has dealt with CSV files and text files and other garbage? It stinks. It's uncompressed. Uncompressed data. And sure, you can compress it and move it around, right? It's still a pain in the neck. Parquet is natively compressed. You don't have to compress it further. It's already compressed. And that's a really nice thing. So this is an open format. It does a lot of the things we talked about already for us in a file. So I show this image here. It's lifted right off the Apache Parquet documentation. I'm not going to be shy about that. They did it better than I can. I adjusted it a bit to make it a little fit here nicely. But basically, all that really matters here is the metadata and the row group structure. So on the left here, you see row groups. Sound familiar, right? Your data in each Parquet file is broken into row groups, which is a chunk of rows. And a Parquet file can have more than one row group inside of it. Each row group will then have data for each column stored separately in what's called a column chunk. Each column chunk can be written to data pages. The data page is the minimum unit of compression. So in a Parquet file, each page can be compressed differently, which is a little different. So a column chunk is kind of like a segment from Columnstore world. And within that, imagine if your segment can be compressed different ways. That's what happens here. So you can have a column chunk be compressed differently in each page underneath it, which is kind of cool. So you get some pretty nice compression because of that. Each data page has a header with metadata. Each row group has metadata stored in the Parquet file. And all that metadata, just like with Columnstore indexes, is used to tell the engine using this data how to use it. Because at the end of the day, if I have 10,000 Parquet files, I don't want to read them in their entirety to get out data from 2 of them. Instead, I want to interrogate the metadata, find out where the things are that match my filter predicates are, and then get what I want to get, and that's the metadata. So column chunk is like segment. Pages are like pages. And row groups are like row groups. That sounded really silly. It sounded better in my head, but whatever. Anyway, there's different kinds of pages, and this is going to, again, sound very databasey in nature, because ultimately, this is stored in a very similar fashion. So data pages store data. This all sounded better in my head when I thought this out. You have dictionary compression in Parquet files, just like in Columnstore. And so we have dictionary pages, which in Columnstore are just stored in 8K pages in SQL Server. And that's the hash tables for dictionaries. And then you have index pages that store lookup information. So the headers are key. Every page inside of every column chunk, inside of every single row group, has a page header. And that basically tells us inside of that page what's in there. What type of page is it? How big is it? Give me a little bit of a check there to make sure it's not corrupt. And then how is it encoded? So just like in those views, the dynamic management views in SQL Server, here we have encoding details. Was there dictionary compression? Was there run length encoding? Was there value encoding? Was there et cetera, et cetera? How is it compressed? And was there any kind of additional information for nested data types? So if you've used Parquet files before, JSON, less structured data, you're familiar with nested data types, which basically means optional data. In the relational world, that's nonsense, right? You have nullable columns, obviously, but I can't simply say in SQL Server, well, in some places the column exists, in other places it doesn't. You don't do that. That's nonsense from a relational database, but in a file structure, it makes perfect sense. Excuse me? Nope. I will talk about it a little bit more in a moment because it's kind of different. It's literally an optional piece of data that can be there or not at all. So it isn't even sparse. It's like in some data pages, there'll be values for a column that exists. And in other data pages, the column simply isn't there. And so you can have nested data types where you have optional fields. I'm not going to talk too much about it. That's more of like just a how do you write data than a how do I compress and optimize it. But it's just something you find in Parquet, and probably shouldn't have even mentioned it, but now I have, so I've opened that can of worms up, haven't I? Index pages are stats, basically, for Parquet files. They tell us at a column level and at a row group level, what do we have inside of our Parquet file? That's our metadata. And so you get information about column stats, and those are key for predicates. So for each data page, that's an index page, it'll tell me for each row group and for each page, for each column chunk, what are the mins and maxes, nullability, and all that information. That allows my filter predicates to do their thing effectively. And then the offset index tells me, all right, where do I have to go and get that data? So the data is often data pages. This tells me where the data is going to be so I can get it. And again, those min and max values are intended for if you sort your data, if your data goes in an order, because again, just like Columnstore, if I insert data and I create Parquet files, it's not going to think ahead and be like, well, you have a billion rows going into Parquet files. Let me carefully put it in the right order for you to opt. No, it's not going to do that. It's going to shove it on in the order you give it, and that's life. Just like Columnstore, and that's fine. But if you do order your data, or if it's naturally ordered based on time, you'll get all the benefits we talked about earlier, which are cool. So nested data types are essentially an optional data element. That I started mentioning it before. It literally just means that you can have a column that exists in some places, not even a column, just a value that's here and not here. That's all it is. And you need to have some metadata that describes what are the definition of. You can actually have like a data type, then underneath it some optional values, and they can even go further with more optional values and so on and so forth. And this sounds like nonsense to anybody in database world, but for a file, if you're used to JSON format or XML, it makes more sense. Just think of it like that. But the metadata basically tells us what's inside of it, how many levels is it deep, what kind of values are stored there, and so on and so forth. If you're going to store weird optional data, you've got to put this all into a bitmap and reference it. So that's all this really is in the end, is what optional values are there. In general, this is not something you use much, but you can if you want. If you're importing Parquet from other worlds where it wasn't relational, it was eventually consistent, it was JSON-based, something like that, then you may have a lot of this. Or you may not. I only mention it here because it exists, and you may run into it, and it's not scary. It's just a way of storing data. But it's not fundamental to understanding how all this works. It's just kind of an aside as to this exists. If you see it, this is what it is. The metadata is key. It's stored separately from the data. That way you can read the metadata first and make decisions. Just like Columnstore indexes, you don't want to read all the data first and then decide what you want and throw it away. You want to check your metadata, which is accurate. Just like in Columnstore, this is not stats that get stale. This is accurate information that tells you exactly what's in the files when they were compressed. Exactly. So it knows. If the metadata says this column contains values from 27 to 50, it contains values from 27 to 50. That's it. If your filter predicate says, give me value 25, it will skip that data because it knows it won't be there. Done. The minimum read within a Parquet file is a column chunk. So even if you have many pages and they're all compressed differently, it'll still read a column chunk, which may contain many pages, of which you may not even need them all. But it can at least from there determine which pages you need and don't need once they're in memory, and you can use them from there. So basically, when you query Parquet files, what happens? You will first say, check the Parquet file metadata, the top-level metadata to see what's in there. What do the row groups contain? Then check the page metadata to see which column chunks do I need or not need. And then load column chunks in memory that I need and execute the query. Again, this is kind of familiar to what we did earlier. You had row groups and segments. This is very, 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 very similar, but in a file format. One nice thing about Parquet is you can customize it, which is kind of cool. And again, depending on your implementation, where you are, the way you do it will vary. But there are defaults for how big your data pages are, for how big your row groups are, and you can customize them. You can also customize your compression algorithm, anything from nothing to using different compression algorithms. These are things where you can go with all the defaults, and they'll probably be great. Or if you have a very, very monstrous amount of Parquet files, you can toy around with it a bit and play with it and see if you can get it more efficient. In my personal testing, I found you can get some gains by changing compression algorithms and adjusting sizes of data pages and things. I've had some fun with it. But you won't see dramatic changes unless you go from like uncompressed to compressed. Obviously, that's going to be a big difference. You can have uncompressed Parquet files. I don't know why you would do that, but you could. It's doable. So you have the ability to customize, and the customization is cool. So how does Parquet compression work? It's not just data. We want to compress our data. This is important, just like Columnstore, compression. There's lots of encoding methods. We have run length encoding. We do lots of things. This is all very familiar. In fact, most of the compression is exactly the same. You have run length encoding. You get rid of all your nulls. You have dictionary encoding. You have bit packing. It all sounds familiar. We ran through all the demos earlier. Compression is applied at the page level, which means that a single column chunk can have data compressed in different ways, which is kind of cool. And therefore, the implementations might be a little different, but the way things compress will be very similar. There's really only one algorithm worth discussing that isn't in Columnstore, and that's delta encoding. So delta encoding is kind of a unique, it's not unique, but it's a compression algorithm in Parquet that is not in Columnstore. And essentially what it does is it takes consecutive values, analyzes them, and says, hey, if the delta from value to value is small, compute the deltas, store them, store the initial value, and call it a day. And that can be very efficient. This is great on data that doesn't change much, or data that goes up and down, like you have values that move but don't jump. And so you have a small range. This has nothing to do with delta lake. The word delta is here. Nothing to do with delta lake. Delta encoding is an encoding algorithm. Nothing to do with delta lake. Just worth mentioning. Here's what it looks like. This is a little awkward to look at. I apologize for math and awkwardness. But basically what's happening here is I have a bunch of values, and they go up. Looks almost like an identity column with some repeated values or missing values. But basically, the values don't change by much. They might be big values, but they don't change by much. And so value encoding would work great in the Columnstore world. Value encoding doesn't exist in Parquet, but we have this instead. And what this will simply do is store the initial value. Then it'll store a relative delta, which is what I need to zero it out, because you can't have a negative value in a bitmap. That will make my head explode. Don't do it. If you want fun, go into SQL Server and get a negative number and put it into a bit column and bitwise it and see what happens. It'll be fun. You'll be confused a little. It does make sense when you think about it, but you don't really want to do that. And then it'll store the bitmap. It'll store the relative delta, and then the actual delta value. And in this case here, you can go from 131 bits down to 52 because the deltas are small, right? They're all numbers from 0 to 11 instead of values from 1,000 to 1,025. And you store the bitmap data separately. Luckily, bitmaps are small. So this is a new encoding algorithm, not new, but new to us, and it's unique to Parquet and some other formats out there, but it's not in Columnstore. So I only bring it up here because it's relevant. One additional note, which is kind of cool, is that a page can be broken up into what's called mini blocks. And so you can actually delta encode within a page with some variance, which is kind of cool. So it's a very flexible algorithm that accomplishes kind of what value encoding does in Columnstore, but differently here. Deep breath, a little bit of math. One additional encoding, which is based on that, and is called delta string encoding. It's basically exactly what I just talked about for strings. And it's going to look really, really weird, but it actually makes a lot of sense. And so essentially, what do you do when you have strings that don't repeat, but they're alphabetized or have common prefixes or things like that, which isn't that uncommon, honestly. This happens very often. You optimize, you order your data, and suddenly you have a lot of values that are similar in a row, but not the same. For strings, that can become very hard to compress. That's what this is for. It's for sorted, alphabetized string data, and it normalizes common characters, kind of like this. I made a bunch of stuff here, and this is going to look weird, but what essentially happens is whenever there's a common prefix, it normalizes, in quotes, it away, and stores the suffix. And you're probably wondering, how did I go from 72 bytes to 47? And the answer is simply taking all the prefixes out and storing them as kind of a delta encoding. So it's exactly what I showed earlier, but for strings. And this is not uncommon that strings do not repeat, but they have common prefixes. So it's worth mentioning that this is something in Parquet. It's not in Columnstore, but you'll see it in Parquet files. And it allows strings to be encoded really efficiently when there's no repetitions. You could have a million strings with no repeated values and still get some nice compression out of it if they're alphabetized. How do we alphabetize it? Well, we've already talked a bit about data order earlier and VertiPack optimization. We'll come to that more in a bit in the world of Delta Lake and Parquet as well. Are there any questions so far about the Parquet format? Yes? Yeah, I left the suffix out. Thanks. I did it. I will fix it. I did check my work, by the way, on this. I didn't notice it, so I apologize. So there will be 2 more bytes. So the suffix length total now will be 49 instead of 47. But good catch. I will fix it. Well done. You have very astute eyes. I do appreciate that. Predicate pushdown is kind of like segment elimination, and the idea here is that you don't want to read all the data and then filter. You want to check the Parquet files, apply filter predicates, and read only the column chunks you need to read, because either I'm not querying all the columns, in which case I don't need them all, or my filter predicates are saying only give me a small range, I can ignore the rest. And so predicate pushdown is essentially analogous to segment elimination, and this allows you to skip whatever you don't need, which is really important. Now again, you still have to read Parquet files and interrogate the metadata, but you don't have to actually read all the data pages and pull all of that into memory and then look at it, because that would be prohibitively expensive, right? If I have a terabyte of Parquet files, I can't read a terabyte of data to satisfy one query and then throw most of it away. I need to be able to check the files and say, which files do I have to read? And of those files I have to read, which column chunks do I have to read? And of those, which pages will I need? Because even if I read the column chunks in memory, I don't want to actually process pages unless I need them. And so there's kind of those stages you go through to try to filter out as much as possible. And this benefits from ordered data. And ordering data in the Parquet world is no different than in Columnstore. You're in charge of it. It won't do it for you. You have to do it. But luckily, most data orders naturally on date and time. And if it doesn't, you can deal with that separately if we need to. And we can talk about that in a bit as well. That's Parquet and how Parquet stores data. And I can go a little quickly because the way it stores data is about 95% familiar to us now. It sounds kind of like Columnstore, and it actually is very, very similar. But Parquet is basically a static file format. If I write data to Parquet files and I want to change it or add new columns or do anything at all to modify it, it's going to make new Parquet files, and that's it. That's all that's going to happen. If I'm only using Parquet, it's going to keep creating more files whenever I make changes, and that can get expensive. If I do updates and deletes and things like that, I'm going to be creating mountains of new Parquet files and then getting rid of the old ones, which is expensive. And so to deal with that, we have Delta Lake. Delta Lake is basically storing your data in Parquet files, but I want to have a bit more of what the transactional world gives me. I want things like ACID, atomic, consistent, isolated, durable, transactions. I want the ability to have concurrent writes, because if two people try to write at the same time, I don't want infinite waiting. I want time travel. This is kind of a cool thing we don't get in the SQL Server world. I want time travel. Well, you can build it in with temporal tables or something like that. But I want the ability to go back in time and look at an old version. And this is all kind of cool and doable in Delta Lake. This is also an open source format. It's basically Parquet plus a transaction log, and it's open source, which means if you have Delta Lake stuff here and you want to put it over here, you can do that. No big deal. If you're storing data in data lake houses, if you're putting it in Fabric or Synapse, this is going to be your default storage format unless you explicitly are putting it somewhere else. This makes the most sense for it because it allows you to have transactions and make changes, and those changes will not be expensive. If your data is very static, like I insert it, I create it, and I'm done, and that's all I ever do, then maybe you don't really need this. But it also won't do very much either to have it. So how is our architecture going to look? The first piece is everything we talked about already. The first chunk of Delta Lake is a bunch of Parquet files. So you have your data. It's still stored in Parquet files, just like before, no difference. You can partition in Delta Lake, which is kind of nice, and that allows you to store separate folders, partition, and have, just like in SQL Server, partitioning. What do you partition by? It's up to you. If your partitions are too small, this is like our knowledge of SQL and databases. If your partitions are too small, they'll be undersized, and you're going to have lots and lots of itty-bitty partitions to read. If they're too big, you're reading a lot of data, but you can partition. And it inherits all those conventions from earlier. So everything we talked about already, about Parquet, we get all of that. Plus, more. More is good, right? So now we have what's called a delta log. The delta log are all the changes. So I've made transactions now to insert data, update data, delete data, merge data, add columns, remove columns. Any changes I make to my data will get logged in the delta log. And that's just a ordered by time list of all the transactions. That's it. And to optimize that, Delta Lake will include checkpoint files. Checkpoints are familiar to us through the transaction log in SQL Server. It's not that different. Checkpoint files are Parquet files that summarize transactions and simplify them. So if you do a transaction that is very repetitive in nature, that is redundant, something like that, it will clean it up for you and make it smaller and simpler. That allows you to summarize longer periods of time without reading a very, very long transaction log. So it'll do everything it can to simplify and shrink the data down, and because it's in a Parquet file, it can be all compressed and made small and efficient. Are there any questions? I'm just going to ask every so often. Yes?
So you get like one delta log per table and one checkpoint file per table as well, or is a checkpoint file for all of them?
Good question. The answer is you'll have lots of delta logs and lots of checkpoints that are created over time. I have a little image of it shortly. When I get to the image, I'll show it to you. But no, you don't have just one. That would be humongously ridiculous, and reading it would be awesome in a bad way. Awesome in a bad way. We don't do that, luckily. All right. So deletion vectors, what does that sound like? The delete bitmap in Columnstore. So again, just like Columnstore, data gets soft deleted because cracking open a Parquet file, rewriting the whole thing plus all the metadata for all the pages and all the row groups and everything takes a while. And we don't want to do that, especially for a lot at once. So when you delete data, it's going to create new files called deletion vectors and store that metadata separately. And when you read data, it's going to interrogate the deletion vectors first and then ignore those rows from the Parquet files. This is just like what we talked about earlier, Columnstore. Exact same idea because it's faster to do that than decompress, recompress, decompress, recompress. And then there are additional optimizations we'll talk about later that will clean that up for you as well. Because you're probably asking yourself what happens to that data later. Yes?
So just so I understand, one of the promises of Delta Lake is that it can do time travel, that you can go back and that sort of thing. So I assume then that these deletion vectors have to be logged and it has to read all that to tell, okay, what was deleted when? Is that accurate?
So the question here is with time travel and deletion vectors, what do we do with all that to store it and manage time travel? And so it's going to maintain all this information in the transaction log over time. And you can specify in Delta Lake a retention period for your data, which is important. You want a retention period. You may want to keep it forever, but that can get big, and not everybody wants to pay for forever. But you specify a retention period, and when your data rolls past that, the old transaction logs and all the old stuff goes bye-bye. But you'll maintain all of that metadata about what happened and when in the Delta log. The soft deletes themselves can go away later, but the Delta log will tell you what's happened. Yes?
Millions of records that you add every night and you change and delete records every night as well. Those get saved to the Delta logs after a year. Does that affect your performance?
A little, but not really. And the main reason is that just like how you can do a reorg on an index in SQL Server, you can use optimize here, and I'm going to cover that shortly, to clean up deletion vectors and summarize. And the checkpoint files help a lot here too, because the checkpoint files will summarize your Delta log. And so does it cost you something to save all that detail over time? The answer is yes. But it's pretty well optimized to manage it. The idea of inserting and deleting rows isn't foreign to Delta Lake, and it's pretty well optimized to handle that. So I wouldn't worry about that. Just, if you ever do run into latency with time travel, consider retention periods, partitioning. Those are really your solutions to that kind of stuff. Ultimately, this isn't something that should become problematic. This is part of life. If you want time travel, if you want transaction logs, this is how you do it, and you want this. And so ultimately, if you do optimizes, then Parquet files will then get rewritten, which is expensive, but it can then clean out the deleted rows. So now your Parquet files shrink, your deleted rows go away, your data gets smaller, deletion vectors go poof, but still all log though, because you need the logging for time travel purposes. But again, you specify your time travel, and if you want the ability to have ACID transactions, but you don't care about time travel, you don't have to have it either. That's something you can disable and not use if you don't want to. Here's an example file layout. Again, this is a very simple example. I stole it from the Delta Lake documentation because they did all the work for me, and it's fine. I appreciate them for documenting their stuff well. So this is partitioned by day, which may not be what you want to do for partitioning. It could be a lot of partitions. But you can see there's each partition. You have Parquet files with data. And then I have my Delta log stored separately. And the Delta log will simply create JSON files for every transaction. Is that going to be a lot of transactions and a lot of JSON files? Yes, but that's fine because the checkpoint files deal with that. And so in the Parquet files in the Delta log, it will summarize transactions. And again, you don't control this. It controls it, and you want that. It's going to do a fine job of summarizing. That way, you don't have to read every single JSON file. You simply have to read the checkpoints, and it will always maintain the last checkpoint. That basically tells me now. I want a version of my data now, at this moment, which is what we usually want, right? Usually when you go into data, you want now. What does my data look like? And if you want time travel, then you go back. This is kind of how it will look. And you can get into all the detail if you want and crack them open and look at them. There's not too much to see there. But this is kind of the structure of it. And so yes, this is a mountain of files, which if you're used to databases, seems awkward. But it's not that. It's not slow. This is fast, and a lot of the summarization here makes it even faster. So now there's more little things I'm going to mention here that are important. Optimize is what is basically the equivalent of a reorg in SQL Server. Optimize can combine Parquet files. It can get rid of deletion vectors. It can basically clean things up that are in need of cleanup. You can go ahead and it'll create a checkpoint if you want it to. It does a lot of things for you. And that basically is doing all the things we talked about earlier with merge and self-merge, 2019 and above in SQL Server. It's doing all the same things here. It will resolve deletion vectors and make them go poof. And it can do that because your transaction log has all the history. So even though your current version no longer has delete vectors, your history has it. And you can have auto-compaction. Most newer systems, newer versions will have auto-compaction. So if you want to simply go ahead and optimize it once a day or something, or whenever it feels like doing it, you can have it do it, and you don't have to worry about it again. It's kind of like running the once-a-day reorg kind of deal. It's not a bad thing, and it does all this for you. If you do it frequently, the effort is minimal. You also have file retention. This is the time travel challenge of I want to keep a full history for 1 year, for 2 years, for whatever period of time. Eventually, though, I want to clean it up, and it won't do it automatically. Unless you put something together to do it for you, it will keep data forever. But most systems will have the ability to set a retention period, and when you do that, it will automatically apply it. This is needed to clean up your old data. So if you keep 1 year of retention and you have automated retention in place, then you're all set. And again, every implementation is a little different, which is why I'm not going into detail here. If you're in different ecosystems, if you're in AWS, Google, Azure, Fabric, Synapse, Databricks, whatever, it's going to be a little different everywhere, which is why I'm not diving into nitty-gritty detail, because depending where your data is and what systems you use, the implementation is going to look a little different. And you can even do it yourself. You can actually export data right at a SQL server in a Parquet files using Python if you want. They're going to natively support it soon. There's a private preview right now for Open Rowset to create Parquet files directly from SQL Server, but it's private preview, so you can't do it yet. But soon, which is good because I don't want to write to CSVs anymore. I want to write to Parquet. It'll be way smaller. So, an aside. Vacuum will not improve your query performance. It's only meant to get rid of old data and save storage, or if you have retention periods that are important to a business or an organization for compliance reasons or whatever, poof, make it all go away, and don't get sued. Very important. It will redefine your time travel range, of course. If you have a retention period of a year and a few more days pass and you do vacuum, then you go back to a year again. You can also change it, though. You can at any point change your retention period if you want and say, you know what, keeping a year was too much data. Nobody ever asked for more than 6 months, go to 6 months. And then it will clean everything up before that, and you're done. So this is really for time travel more than anything else. If you don't use time travel, this may not matter to you. If you do, this is very useful. This is going to sound familiar too. Optimized writes basically says instead of writing as a separate process, separate Parquet files from every single writer, I will coalesce trickle-down writes and put them into files and then push them into the Parquet files. What does this sound like we talked about earlier? Anyone? Delta, yeah, Delta row groups, Delta Store, yeah, it's the exact same thing in Delta Lake. And so they call it optimized writes because if you call it Delta row groups, it'll be so confusing. But optimized writes are basically the exact same thing. Essentially, instead of trickling the writes directly into Parquet files and decompressing, recompressing, decompressing, recompressing, creating new Parquet files, doing whatever, making a million little transactions, it will take the writes and summarize them and push them in one operation. And again, this is really meant if you have a lot of writers at one time. That's all. If you don't have a lot of writers at one time, it won't really matter. But if you do, it will do everything in its power to try to trickle them in, summarize them, and write them in one process. This is a really cool feature, and it will speed up your writes. It will reduce the size of your transaction log, and you'll still maintain ACID compliance. So if that's important to you, you'll maintain it. You don't lose it. This simply makes your life better. Not every scenario is like this, but if it is, this helps you out here by basically having a Delta Store within your Delta Lake, which sounds silly, by the way. It just does. One really important criteria, the thing about Delta Lake, is that everything we've talked about so far is version dependent. And this should not be foreign to us. There are many features I mentioned in Columnstore indexes that are version dependent. Like merge and self-merge were introduced in 2019. If you're in 2016, you don't get that. If you have a 2012 Columnstore indexes, you can't even write them easily. You can't modify them. And so depending on your version of Delta Lake, you'll have different features. And so just keep an eye on that. It's useful to know what version you're using, what implementation you have, are you missing features. It's a really simple thing to check, but just make sure you know what version you have because you don't want to miss out on things you want. Before I jump into optimization, anybody have any questions about the Delta Lake format or the Parquet format? Yes?
Just on that optimized writes slide,
Yes.
like there's some daemon analogous to the tool mover, something that's doing this compaction thing.
Yep. Exactly. So in SQL Server, I didn't even mention the tuple mover, but you did. But it's all an asynchronous background process. here as well, and that's intentional. You as the engineer, architect, whatever, do not want to be doing that. None of us do. I don't want to do that. None of us want to be involved in deciding how to write data to a table physically. If we did, we'd lose our minds. And so this is something that the system has to do for you if it's going to work. And so yes, you do nothing. It figures it out and does it for you. And it is implementation dependent to some extent and version dependent as well as to what you get. If you're in a very old version of Delta Lake, you probably won't have this, and that's fine. Again, you don't need this. It just improves the speed of writes and reduces transaction log size. Now, we have the same challenges we had earlier today in that we have Parquet files, and we have lots and lots of row groups inside of them full of lots and lots of rows of data, right? They're files containing essentially rows of data like in a database, but by default, they're not ordered. Now, we had VertiPack optimization in Columnstore indexes. Here we have V-order optimization. Sounds familiar, right? Very, very similar idea. This is something that's basically automatic in most modern implementations of Delta Lake. If you're using Parquet files in Azure Lakehouse, Direct Lake, whatever, this is automatic. You don't have to do anything, it just works. If you're using Spark or other systems, you have older systems, you may have to actually get involved a bit with it, but essentially all it's doing is taking the rows when they write them to Parquet files, and before they write them, reordering them based on whatever will help it compress best through run length encoding. And so it's doing all that work for you. And then after it's optimized, it'll then simply do the encoding and compression and all that good stuff, and it'll be more efficient. The beauty of this is that whether it's v-optimized or not like this, v-ordered, it's still open source, because the files aren't actually proprietary or different. You simply have, I don't know, 5 million rows, 1,000 rows, whatever, and they're in a different order. But the metadata is, the metadata for the top level file isn't going to change. And so ultimately, your Parquet file has the same data in it, but instead of being ordered in a pile of mush, it's ordered by what it believes to be the most likely dimensions to make it compress the best, which will often be date, followed by maybe like an account key or something like that. Again, I'm just guessing here, but those are the most common. You start with date, and if there's really any more order to do, it'll probably be by some account ID or person ID or something like that. It isn't always like that, but it often is. And so if you're in a modern system like Fabric, this is just automatically enabled. You do nothing. You insert data, and it'll magically get ordered to be more efficient. Just like VertiPack optimization, it works, and that's good. Again, you as a person developing analytic frameworks don't want to be obsessed with details. None of us do. We don't have time for that. So it's got to do it for us to be effective. You only go to the details when things go wrong and break, and then you deal with them. We all do, right? But that's life. Yes?
You were talking about the order. We use, I don't know if you ever heard about Datable.
OK. OK.
Anyway, for the business key, you create a hash key. So wouldn't that affect the order? Because we are migrating to Fabric right now. So maybe using hash keys as a business keys is not the best idea for the Fabric.
If there's multiple rows by the same business, they get the same key?
No.
Oh. Does date still matter? You still have date stamps and everything?
Yes.
OK. I mean, ordering by date first would be the way to go, I think. If you have a unique hash key in every row for a business, then that's not going to compress very well or be used in ordering. But it'll probably start by ordering by other columns first. So that hash key is not going to compress well, but everything else probably will. And so you take a hit there. Is it that big of a deal? Maybe, maybe not. I wouldn't worry about it unless you run into performance problems. Honestly, I would go ahead and create everything, see how it performs, and if it matters. And if it performs terribly, and then figure out a way to deal with your hash key and make it better. And again, there's lots of ways to deal with that. But I would try it first, see how it works, because it will still compress your files really, really well. You just may not get ideal scenarios with that one column. But you need a way to look it up, though, right? You need a way to actually look up by business. So you need some way to code it with a decoder ring. And as long as that's in your predicates, you're OK. So your filter predicate has that in it, you're good. But wait, there's more. In the same way that in SQL Server you could have a non-clustered column store index, that covers your secondaries, right? So in Columnstore world, you might have a clustered row store index, but you might need more information. Or you might have a clustered column store. The most common scenario is I have a clustered column store. It's ordered by date. I have billions of rows. And somebody comes along and says, hey, I want to get all of the sales detail for the past 5 years for one customer. And you run that query, and it takes like 5 hours, and everything breaks. Because instead of querying by time, you're querying by a new dimension. And so in the column store index world, the solution to that would be to have a non-clustered row store that allows you to order your data and have a pointer back based on some other key. You don't really want to do that unless you need it, because again, you may get enough benefit out of segment elimination and VertiPack optimization. But in this world here, in Delta Lake, Z-order optimization is basically the same thing. It's called multidimensional clustering. It sounds fancy, but all it really is, to keep it the simplest term possible, is it's kind of like a non-clustered index for your Delta Lake tables. It basically allows you to order by some other column besides whatever your natural ordering is. If your natural ordering is good enough, and again, you don't use this unless you need it. These are features you use and you need them, but if you don't need them, you don't need them. And very often, ordering by date is good enough for most systems, but if you then run that rogue query that says, get it by salesperson, get it by account ID, get it by employee ID, then it's going to have to read everything potentially if there is no natural ordering with that key. So when you create Z-order optimization, this is essentially going to take and it's going to create a new ordering of data based on some other column. And it's compatible with V-order optimization. It's basically an additional way to document your data and order it and be able to query by other dimensions if you need to. If you don't need it, don't worry about it. If you do need it, worry about it.
Where is that stored? Is that stored in a Parquet file or is that stored?
This will all get stored. Essentially, ultimately, it's going to be co-located data. There's no magic here. You're creating more data. So you're creating more Parquet files to store your data. There is no magic. You're storing more data. And honestly, if you create a non-clustered row store in the SQL Server on top of a clustered column store, it's going to take up a lot more space too. So there's no magic. There's no freebie here. It does cost something to store this, and that's a whole lot more Parquet files. But if you have a use case where you need to query by a dimension that's just off the walls and there's no natural ordering, you need to do it, right? Like you don't have a choice. And this will be faster than not having it. You know, reading all the Parquet files every single time is going to hurt. So this is the alternative. But there are additional optimizations. And again, it depends on what implementation you have. But one of the newer version of this is liquid clustering. And so with Z-order optimization, you've got to choose keys. You've got to maintain order and do a whole bunch of stuff to make sure that it actually works correctly. With liquid clustering, you can redefine additional clustering columns automatically. And so this is really what you do when you have variable workloads and people are throwing curveballs at you all the time. And so you don't know what predicates are coming down the line, and they're all over the place. And you want to try to do your best to predict query predicates and not have things break and take forever. And again, things won't break. They'll just take a long time, and nobody wants to wait. And so you can create multiple clustering columns, and it will create metadata for each column separately. There's a limit to how many, but you can do a lot of them. And so instead of having like a single non-clustered index, it's kind of like a non-clustered column store in the Columnstore world, where each column is stored separately, has metadata, and you can work with it. This is better, though, because you get enough metadata where the order doesn't actually matter as much now. So you have ordering by multiple columns. So this is kind of the last natural evolution of all these optimization techniques, because it allows you to, the cost is space, of course. You're storing more data in more ways with more metadata. It's not cheap, but if you need it, you need it, right? If you have mountains of Parquet files and people query it in different ways, this is the solution, and you would far prefer this to having people wait forever. And also, you know, your bill go up too. You're making the bill for storage is expensive, but the bill for all the compute to run expensive queries is going to be more expensive. Sure.
The liquid cluster, is it something that is created for you by the engine, or you have to create it yourself?
If you're using Fabric or a modern engine, it's going to do this for you, which is good. You can step in and nitty-gritty modify things and make changes and muck with it, just like a lot of other implementations of things. But if it's available, it can be you can tell it what columns, and it'll do everything from that point on automatically. You probably want to at least, it's something if you don't need it, don't create it, because it takes up space. And so I would say the best thing to do here is if you are having slow queries, investigate, add this in the columns you need, and call it a day. It won't automatically enable this for you and do it for you and pick columns for you. I don't know if you'd want that, because it will. Correct. You could pick a lot of columns, though, and then from that point on, it's going to do the work for you. So you tell it what to do, and then it will do it for you. And from that point forward, you're done, and it's going to handle it for you. But you have to tell it which ones, because it could be expensive, right? If I have 100 columns in a table, and it automatically chose 25, that's a lot of data to rewrite. And so you don't want it to do this unless it's needed. And so it's one of those things where you probably won't even create this until you run into a problem, at which point you can do it. And one nice thing is you can add more columns to it, and it's not going to be some giant rebuild situation. You can add additional columns, and it will create that for you and keep working.
Sorry, but we run into a situation where we are moving our data to Fabric. Then we are torn between, the dimensional modeling process or strategy, and trying to determine how we're going to benefit in terms of performance. Using the semantic model, it's a layer on the lake house. Or if we thinking of having a flat Parquet file with all the columns that we need, and then querying it, using the semantic model, because eventually we're going to use Power BI. So maybe it's out of scope for this presentation, but with this presentation, what you just said, is it more performing to use this type of clustering and clustering to create the semantic model on the lake house, and is it going to be more performing, or we have to just create different segments or dimensions based on business use cases, so that we can create the relational side in Power BI?
So the question is essentially, depending on workloads, what's the best way to implement? Should I normalize some data? Should I create dimensions and facts? Or should I create liquid clustering on top of data to try to figure out how to make it work with filter predicates? And the answer ultimately is going to be on what kind of workloads you expect. If you know exactly how it's going to be queried, you could use liquid clustering to solve the problem, give it all the columns you want, and it will do the work for you. If you truly have a giant data lake and you have no idea how it's going to be queried at all, you have no clue, and it could change, then you may have to just kind of figure it out as you go, which I know is a terrible way to say it, but you've got to basically know your workload to know where to go. And this is where it can go from being a data lake to a data swamp. But the lake house ultimately is, you have your lake and you have your nice clean warehouse on top, and you may simply be hitting each one separately for data. If you have very, very well-structured business use cases, that sounds kind of like a warehouse. If you have very unstructured, I don't know what I want, give me the raw data, sounds kind of like a data lake. And so the answer is you may need both if both use cases are heavily part of what your organization does. So you may need both. It's really going to depend on what your organization needs, I think, and I can't give you a decisive answer because I don't work for your organization. I could, but that's also out of scope of this presentation, is me working for your company. Just saying, out of scope. But great question, and the answer may be best of both worlds, but it'll depend on your organizational needs. But great question, though. Thank you. Yes? Oh, that's awkward. OK, there we go. Thank you. So this is not really a versus. I put this here only because people ask this question every single time. And so instead of you asking it and me answering it, I'll just answer it right now. Why would I use either one of these over the other? And the answer is it really depends on your workload. In general, if you have a scenario where you simply write data, like I insert data, and that's all I really do is I just insert data, create data, done every day, which isn't that uncommon, right? There are many workloads where you simply do a daily load, and then you're done, right? Every day I load data, done. Daily load data, done. If that's your workload, you may not need the Delta Lake architecture. You may want it, and it's the default in a lot of applications, but you may not need that, and having a pile of Parquet files might be fine for storing your data. It really depends on your workload. But the moment you need additional features, like you want transactional support, you want ACID, you want time travel, you want versioning, if you have lots and lots of trickle data loads, incremental loads, if you have lots of deletion and writes, then you want Delta Lake, because it handles all of that. This is really the difference between Columnstore indexes early on, where they were practically read-only things you created once, or the ability to do all the cool stuff we talked about earlier that makes them efficient. And so more often than not, you're simply going to use Delta Lake, because the nice thing about it is that if you use Delta Lake, but your use case is super, super simple, like I just do a daily data load and I'm done, you're not going to have mountains of JSON files. You're not going to have mountains of checkpoint files that are huge. And so at the end of the day, the amount of effort that goes into it isn't going to be that big. There's still some more overhead, but it's not that mountainous. And so you may be happy simply having it in Delta Lake and calling it a day. The nice thing is you can migrate back and forth. You can take your Parquet files that you have from one system and move them into Delta Lake, and then begin using the transaction log there and get all those features. Or if you have a Delta Lake and you want to bring them somewhere else where all you want is the Parquet files, you can do that too. Both of those are supported migration paths. These are open formats, and so you can just do that. And that's kind of nice. If you have them in Azure, you can take them out of Azure. If you have them outside of Azure, you can put them in Azure. And I've done demos of that in other presentations before, where I've actually taken Parquet files out of SQL Server or out of on-premises solutions, and then pushed them over into Fabric or Databricks, and started using them. Yes?
If you're wanting to join data between Parquet files and Delta Lake, can you do that, or do you have to export the data that you're going to use out of Delta Lake to Parquet files or something like that?
I almost want to say that it depends where it's stored. If you're just putting it all into one lake or something like that, then it really doesn't matter. It's all the same bucket of data. I don't want to say it's all the same, but you're storing data in two places or in one place. And if it's in one place, it doesn't really matter. It really doesn't. It's really going to matter where's your data located and how are you getting to it. But these are still open formats, and they're read the same way. I mean, you read Delta Lake the same way you read Parquet files, just there's more stuff to read, that's all. But I don't want to say there's no difference, but it's really more dependent on where you put your data than on what technology you're using under it. So the migration back and forth is nice, though. Yes?
Can we do the alter table drop column?
Great question. Is it my next slide? Yes! All right. Great question. The question was, can I do alter table, drop column, or something like that? And your timing was like you're almost like a planted audience member, but I know you aren't. So that was awesome. Thank you. I'm going to start bringing things together now. We have like 25 minutes left, and I want to bring everything together. And the first thing I'm going to talk about is exactly that. This is called schema evolution. And essentially, what is it? Schema evolution is where we want to take and change our schema. We want to add columns, remove columns, alter a column if it exists already, things like that. Now, in Columnstore, it's actually pretty straightforward. It's fast. The only thing in Columnstore that will not be fast will be if I alter a column and make it smaller or put a default value in or not null. And then it has a whole bunch of validation it has to do to be transactional in nature. But in general, the complexity is not huge, because if I add a new column to Columnstore, it makes brand new segments. So brand new segments mean new structures. All the existing ones don't get touched. You also need new metadata, but the old segments just stay where they are, and you don't muck with them. If you're in Parquet files and you're just in the Parquet format exclusively, no Delta Lake, this is messy, because you have Parquet files that have 10 columns, for example. And now I begin adding a column. It's not going to go back to all the old Parquet files and fix them for you. You're going to begin making new Parquet files that have a new column in them that the old ones don't have. Now, most modern technologies will do schema merging and resolve it, and you don't have to worry about it. It'll see, OK, I have 10 columns here and 11 here, 10 have the same name, I get it, and you're fine. But if you make enough changes and rename columns and do things like that in the Parquet format, you very easily can get into a situation where you mess up how you're able to read your data. And so if you're going to make a lot of schema changes and you're storing data in Parquet, it could be worth going back and rewriting your old files to add the columns in, just so that things make sense. You don't have to, but if you're like renaming columns, for example, that will get confusing fast. Delta Lake supports a lot of this more natively. In the Parquet world, it's very implementation dependent. In Delta Lake, this is still a little implementation dependent, but it's more native. And so things like type widening or automatic, you don't have to really worry about it. If you make changes to your schema, that'll all be in the transaction log, and that's OK. So you get a little more flexibility here. It's not as scary. You can alter table, alter column, and it won't blow the world up. And so if you're going to do a lot of that, though, if you know that your schema is very variable, software releases go out really often, you might want to have Delta Lake just so you have a little more understanding of what changed. Because at least then you know when columns changed and how they changed, as opposed to like, I have 1,000 Parquet files and they all have different columns in them, which you can reconcile that, and apps will try, but it could be kind of confusing, especially if you rename. If you're renaming columns, you've made the world confusing. I would advise against that in general in this world because it's going to be confusing. Now, here's a fun question. How about proprietary tools? I have data in something that is closed source, proprietary, like Snowflake or Tableau or whatever, and I have no flapping clue how the data is stored at all. They don't tell me. They'll give me some sales figures and information, but I don't really know how it's stored. Guess what? What do you think? It's just like what we talked about here. It's going to be Columnstore plus a pile of stuff that they proprietary throw on. They may throw it in memory. They may throw it in NVRAM. They may do a bunch of stuff to make it faster and faster and faster. At the end of the day, they're storing it the same basic way with a lot of the same optimizations. And the only real difference is they're going to charge you more money for it, which is fine, because if you use a platform, you use a platform. That's life. Not everybody wants to do their own stuff. That's fine. If you like Tableau or Snowflake or Iceberg or whatever and you use them, great. But know that even though they're closed source, you don't have full insight into how they store the data, it's everything we talked about for the past hour, 2 hours, whatever we've been here for. It's all the same. I went ahead and I did a little bit of screenshotting, and I lifted a whole bunch of stuff off the Snowflake webpage. See? Isn't this cool? I lifted all kinds of stuff off there. You can chuckle at this. All of their selling points for Snowflake. Highly compressed, advanced, new SQL query engine, metadata management, authentication, access control, query parsing. What does this all sound like? It's everything we talked about already. That's all. And so what does this mean? This means that no matter what proprietary platform you're on, if it's a modern data platform and not something archaic from 20 years ago, that all the optimizations that we're about to talk about apply to everything. Which means we can now apply best practices to everything. And this is the all the things, the all the things t-shirt. All the things we can now apply to. Number one, and these are now best practices for every system we're talking about here, whether you're in Delta Lake, Parquet, Columnstore indexes, Snowflake, somewhere else, it doesn't really matter anymore. Number one is trickle inserts kind of stink. Inserting data 1 row at a time, 10 rows at a time, 1,000 rows at a time in small batches to avoid locking and blocking, that's transactional world. But this is analytic land. It's a beautiful place. It's very different. It's not always beautiful, but it's different. And in this world, inserting data in larger batches makes sense. If you have bulk insert functionality, use it. But even if you don't, there's no benefit in spamming your log with 1 million inserts. If you have 1 million rows to insert, just insert 1 million rows. The engine will do it for you in a beautiful fashion because you'd rather have 1 transaction than 1 million. In general, trickle loads will be slower because they're all going to have to use Delta Store-like structures to stage your data and deal with the fact that you're just mountainously shoving rows down its throat constantly, as opposed to saying, here is a nice pile of data, enjoy. Because that's easier, right? Like if you eat a bowl of Cheerios, do you really want to eat it 1 Cheerio at a time? Or maybe have some spoonfuls, or if you're like me, I'll empty the bowl in my face. But that's a real bulk insert. But anyway, your goal here is to not trickle insert. There's no benefit. This is like the best practice we mention everywhere on planet Earth. It still applies here. No matter what system you're in, only call back the columns you need. Because at the end of the day, everything is stored by column for analytic data. If it's not, get a new storage engine because you're old. Your system is old, not you. But columns can be read independently from each other. If I have 50 columns and I read 3, I can ignore 47 columns. And so therefore, you don't want to select star, and you don't want to select more columns than you need. If you have the ability to pick and choose columns, do it. You will save a lot of time and a lot of compute and make that monthly bill a little cheaper. And one caveat is if you have order bys or where clauses or group bys that are unnecessary, it will actually create more reads. This is actually a little different from transactional world. If I'm in transactional world and I have a filter predicate that filters me down to 1,000 rows, and then I have an unnecessary predicate that does nothing and I still have 1,000 rows, it's not going to change much. Your execution plan will get a little different, but not much will change. In this world, though, it now needs to read that column in order to satisfy and check it. Yes?
How about the query with the dumps and joins the idea
Every column that so the question is, what do you do when the developers write the query with 1,000 joins? In analytic land, like here, every column that you join on has to get read out of whatever your analytic data store is. And once it's read, you can then validate the join, kind of like a filter predicate, and go from there. And so the more columns you join, the more data you have to read, and the more painful it gets. And so you benefit from joining less columns here. If you can't help it, you can't help it. But every column that you filter, join, group by, having, order by is one more column you have to read. So if you don't need it, don't query it. One more question, yes?
Anything like query store that can go back and say a user might misbehaving queries in this, or do you have to, I don't know how you'd even do it if you didn't have a way to.
The answer is generally going to be no. The good news is that in analytic world, we usually have more control over our queries, and we can understand where they're coming from. If something is slow, a person's going to come to you and say, my dashboard's slow, my report is slow, my thing is slow, at which point you can look at it and begin walking through all the best practices and figuring out what's wrong with it. You can use Query Store and SQL Server, and it will monitor Columnstore indexes, but it won't give you a ton of information comparatively, only because there's less to do there. Like it can't recommend new indexes for you on Columnstore. It can't do a lot of the things it can do for RowStore. But you can have Query Store to monitor at least the timing of queries. So if a Columnstore query is slow, it will log that, and that information can be useful. Yeah, you're a little more on your own here. I think in analytic land, you're very often relying more on the consumers to tell you when things are slow. And I'm not messing around and joking here. It's really just how it works. Like if somebody's consuming data at a large scale and it's slow, they're going to tell you. And they're not usually going to be end users like using an application. It's going to be more internal people running reports, dashboards, AI, ML, whatever. And they're going to have comments for you on speed. So we've got about 15 minutes left, and I do want to go through best practices. They're really important. These are great questions we have here on how do we find bad queries and deal with them. I mentioned this earlier twice. I'm going to mention it again. Across most platforms, update operations are going to perform poorly because an update is not the same as delete and insert in analytic land. Here, it means you have to do things like delta store kind of things, or the deletion vectors, or all these special optimizations to work around your horrible query. It needs to do them here, but all at the same time. And so as a result, when you update data, it's going to be painful. In Columnstore, it's going to be slow. In Delta Lake, it's going to create a lot of transaction log. And in Parquet, it's going to make all brand new Parquet files. And so wherever you're doing things, you're actually better off by taking an atomic delete and an atomic insert instead of having an update. It's simply computationally expensive, and analytic systems simply aren't meant for updates. Even in a slowly changing dimension table, you're better off doing delete and insert. And it does sound silly, but it will be faster. Because ultimately, updates will bypass a lot of the optimizations we talked about in order to maintain a transaction. It's just painful, no matter what system you're in. So be aware of updates. Avoid them if you can. If they perform badly, just replace them with delete and insert. Call it a day. If you have key columns that you can order your data by, do it. Almost always, your key column is going to be a date time. I have a sample date. I have an order time. I have a last modified time. I have some date time that matters. Order your data based on that and maintain the order over time, which is honestly pretty easy. If you load data over time in order by a dimension, then maintaining that order is easy. If you muck up the order through releases or changes or other stuff, you can reload your data. Even in Parquet world, you can simply say, all right, I'm just going to rewrite all my Parquet files, reorder my data, fix it. It's a bunch of work. But it's also a one-time-ish kind of thing. And again, the old data that isn't being touched anymore won't change. And so you can always partition your data to ensure that all your old data is separate from your new data, you don't have to worry about all that. So if you have older data that's separate, that never changes, you don't have to touch it. Just leave it alone. Life is good. Keep going. But those key columns are important, though, and it's almost always going to be a time dimension to start. If you need additional indexing, clustering, whatever, you can add it as needed, but I wouldn't preemptively do it unless you truly need it. Truly know that you need it. Retention. Everyone forgets about retention, right? It's the last afterthought. The number of performance problems and architecture problems I've had in life that were simply solved by me saying, hey, do you really need data from 20 years ago? And they said, oh, no, we can get rid of anything more than a year old. Really? Delete 10 billion rows. Done. It amazes me how often this happens. If you have retention problems, consider alternatives like archiving your data, partitioning it, hyper-compressing the old data, soft deleting it, interactive it. Do something to separate out the old data from the new data. Store it differently, compress it differently. You know, every major data platform has a way to store your old data, things like Glacier or whatever, where you can just simply put it into cold storage where it's available. It'll be slow, but hey, no one ever goes after it, so no one cares. You know, it's there for posterity. It's there for compliance. Always consider that. Very often, new data and old data are very different. And the older the data gets, the more different it is. And so if you can apply retention in some form, you'll make your life a lot better. Everything will get faster and easier. You'll save money. People will share your life and your existence and give you money, right? They'll throw it at you. Yes?
So Fabric doesn't support partitioning or partition views. Are there specific things for Fabric you recommend to kind of implement that?
I think the easiest thing in the absence of partitioning will be maintaining data ordering, and you can still have retention in Delta Lake. And so that retention can help you ensure that I'm not time traveling for the rest of my life back in time. And so simply maintaining data order will give you what you want. You know, partitioning is really just a way to force it, but you don't need it. Like technically, if you had a mountain of data and it's perfectly ordered from like 1/1/2000 all the way through now, and it's ordered nicely, it'll perform great. And whether you partition it or not, it'll still perform great. Can you get a little more out of partitioning? Maybe, some convenience, but the order is what you're going to lean on then if you don't have it available. But good question. What do you do? If you don't have partitioning, what do? You lean on data order to help you out. And again, it's been mentioned enough already, I barely have to mention it again. If your data gets large enough and you can partition it in whatever system you're in, do it. It'll give you maintenance benefits. It'll help you hyper-compress your older data. You can store it in different places. I can say, hey, my oldest data in these partitions goes in the slow, super compressed stuff over there. And the new data that people care about for the last 2 years goes over here. And you can do that and save money and, you know, save storage and ensure that your data and your SLAs are all met, things like that. Your partitioning columns can change if you have it stored in different tables. You can even say at some point if you want, my new data goes in this structure, my old data goes in a separate structure altogether. And that can allow you to treat them completely differently if you want, which is fine. So just consider the fact that you can partition data, and even if it's big enough, store it in multiple places. There's no rules against that. This is your data. You can do whatever you want with it to meet your SLAs, to meet your cost needs, whatever. If you have really, really big binary data, strings and var binaries and images and documents and all the scary stuff that in general doesn't compress very well, what can you do? And the answer is consider storing it separately. If you can't normalize like a string column, at least store it somewhere separately and reference it. Because at the end of the day, it's not going to compress very well a lot of the time, and you may not want it alongside all the rest of your data. In general, lengthy binary data will find its way into data lakes very often, and that makes sense. You want your detailed data. I have orders with titles and descriptions. The title's kind of big. The description, any column called description is like a varchar max, right? Or an nvarchar max, it always is. And no one ever stores more than 1,000 columns, except for that one person who puts like 1 billion characters in, right? But whenever you have lengthy binary data, think about ways, put your transactional land hat on for a minute, think, how would I fix that in transactional land? And how can I apply that guidance to here? Because realistically, you're going to have a high cardinality column that's really, really long and painful. How do I deal with it? And the answer is going to be ultimately, it's going to break dictionary compression potentially, no matter where it is. What can you do to fix it on your end? And the answer is to try to separate it in some way if you can. You may not always be able to, but if you see compression problems and speed problems, and you narrow it down to the one giant column, just separate it. take your performance problem and put it over here so that most queries perform well and that thing can be over here. It's more appropriate for a data lake. It's not very appropriate for a data warehouse, and it certainly is not going to do great in SQL Server and a Columnstore index. It can, but it may not. Another thing to consider is how is your output going to look? So I'm querying analytic data, and it's going to go to a dashboard. How big is that dashboard? I'm doing some machine learning algorithms. I'm trying to put my data into AI. How much am I actually using? What's it going to look like? Are you just splicing away half the output once I do it? I've seen people pull from a database millions of data points, and then after they pulled millions of data points, slowly plot it in a screen in a chart that was like 1,000 pixels wide. Now, you can do that, but you're throwing a lot of pixels away there. And so do you really need to store and bring all that data back? Could I maybe aggregate the data by the minute, by the hour, by the day, or something like that to shrink the size of the data? Because if you aggregate your data within your storage engine and then pull it out, it's going to be faster than pulling all the data and aggregating it later. You have your I/O cost, your memory cost, your network bandwidth, et cetera, et cetera. Think about that. Because I've seen systems run really, really slow because they're simply saying, well, the output's only 20 rows. Why is it so slow? And it's like, well, you pulled 1 billion rows and then turned it 20 rows later. But that 1 billion rows was slow. So just output size and shape are important. And this is more of just a data architecture note more than anything else. So I want to leave a few minutes here for questions and answers. I know I covered a lot. But the ultimate conclusion to this whole presentation is that it's all the same. All of it. All the analytic data stored in every modern system, they have all their own little tweaks and tricks and tips and things that make it fast, but it's all stored basically the same way. They're going to call them row groups. They're going to call them segments or column chunks or pages or whatever. It doesn't even matter what they call them, but it's the same. It's the same idea. There isn't some fundamentally breakthrough tech that goes past all this. If it's faster, it's probably on faster storage. But the underlying tech is the same. And because of that, when you make architectural decisions about how to store it, where to store it, how to query it, that fundamental guidance isn't going to change no matter where you put it. It doesn't matter if it's in analysis services or in Columnstore indexes or in Fabric or in Synapse or in somewhere else. The basic guidance is going to be the same for all those places. So ultimately, it's up to you to choose the right tool for the right job and then query it as optimally as you can based on all this stuff we talked about for the past 2.5 hours. Boy, that flew by. It really did. And so that's kind of the conclusion to all this. I have further reading here, which I will, all these slides are going to be posted. They're already posted, but I've made some updates. I'll post the updates later. But I have some links here to go back to documentation. I have some white papers here, if you like white papers. I do. You may want some caffeine for those, though. Maybe tomorrow morning you'll read through those. But they're very useful, though. Parquet, Delta Lake, all these formats are very well documented, which is awesome. Feel free to use the documentation heavily. It's very useful. Please review sessions, review the session content, review past summit, review me. This is important. This tells us what we like and don't like, what we did good and bad. Was 2.5 hours of this torture to you? I hope not. Hopefully you appreciated it. But whether your feedback is constructive, happy, sad, whatever, please provide it. It's important. Now, we made it. Coffee time. Does anybody have any questions before we wrap up and go off and have some vodka or something? Yes?
I think you already answered this, but I want to make sure. Databricks, Delta Lake, they seem to push merge a lot. It sounds like merge isn't really the way you want to go with this stuff, right?
Merge is fine until you update. Updating, and it's possible that they may under the covers resolve updates to make them faster, but I tend to avoid them across the board only because I can't control the implementation. And so Fabric may do the right thing, but there's no guarantee other platforms will or won't. And so as general guidance, I avoid updates. I'm not saying to avoid them if you know they work fine. If they perform well, use merge. But just be cautious in other platforms, that's all. Because every platform is different, and in general, the update is the most expensive thing you can do to any data structure. In terms of computational power needed, it's always been the most expensive thing you do. So that's only my caution there. Is I'm not saying don't do it, but be cognizant that in some platforms it's going to be slow and painful. Yes.
So partition Parquet data seems to work best when date is the partition column. We discovered that using something besides date, we really struggled with it. Do you have a quick tip or advice for how to use something besides date?
I always start with date until proven wrong. And then when I'm proven wrong, it's really going to be query predicates. So if people just never query by date, one of two things are happening. Either they have a different predicate, like I always query by account ID. If that's the case, you're going to order by that. Or people never have a where clause. If people never have a where clause, you have a bigger problem. And I would check for that too. If you query your analytic data with no where clause and simply say, hey, give me all the things, it's going to be slow no matter what you do. And so to really optimize your data order, you need to understand the filter predicates. And that may mean reordering your data, or it may mean using a non-clustered index or liquid clustering or some other feature to add added predicates on top of your existing predicate. I like ordering by date by default until nothing else works, at which point then I will consider something else. But I always start with that because it most often works. And then if that plus an additional structure, additional clustering won't help, then I'll consider the initial reordering to be different. But I try hard to stick with date because it's so natural to insert new data that way. But if you can't, you can't, and I get it. But start with that at least, and then go from there. And if that plus clustering doesn't work, then try a different key and see how it works. And I've actually seen organizations store data in two separate structures, one sorted by date, one sorted by account ID. Is that a lot of storage? Yeah, but it may actually end up being cheaper if those two separate structures solve all your problems in one. Simply copying your data to two places may not be that expensive. And so there is that alternative, which sounds silly, but it is a legit alternative, is co-locate your data manually in two places and maintain two structures. Is it crazy? Not as crazy as it sounds. Yes, question in the back. Yes. The question is, when do I choose clustered column store over non-clustered column store in SQL Server? And the answer is going to be, what kind of workload do you primarily have? Is it primarily a transactional workload with lots of inserts, updates, deletes, selects of small row counts? Or is it an analytic workload where I'm doing lots of aggregation and machine learning, AI, dashboarding, reporting, whatever? Your primary use case will be what you use. If you're a primarily transactional workload, do clustered row store with non-clustered column store on top. If you're primarily analytic workload, do clustered column store. And if you have to use non-clustered row store, do it. But I always advise try without non-clustered column store, non-clustered row store first. Do clustered column store by itself first. Try it out. See how it performs. If it's good, great. If you have some filter predicate that's blowing you away every time and slow, then add the non-cluster. But only add it if you need it, because it will, all these additional clustering algorithms that create more data structures on top of your data will cost something. And so just make sure you need it before you, and if you need it, but make sure you need it before you do it. Like, don't preemptively create 10 non-clusters on top of a clustered column store because you might need it. That's going to cost you an amazing amount of storage, and you can measure it and tell me later how it looks. It'll be crazy. So I just urge caution. Yes? So you basically had a clustered row store index, and you put a non-clustered column store in everything? Wait, you had non-clustered, so you had clustered column store and non-clustered row stores on top of it? Okay. Oh, and you had different clustered, oh, I see, okay. So the question is, I have a clustered row store index, and I have lots and lots of non-clustered column stores in all the columns separately to manage small queries. And the answer is the price you're going to pay is going to be on write speed. Ultimately, the more indexes you have, the more storage you need, the longer writes will take. That's your price you pay. and then the benefit will be on your reads. I would consider having less non-clustered column stores on more columns, because a non-clustered column store index on 5 columns, it's not ordered by anything special. It's just it's like an include almost. And so I would consider just I would test having one non-clustered column store in all the columns you need, and then go from there if you can. It would just be simpler, but ultimately you're paying the price on your writes, that's all. So your writes are going to be a little slower because you're going to write all this extra data. If that's acceptable, cool. Ultimately, the real solution is going to be, and I hate to say it, separate your OLAP and OLTP, right? Like your ultimate solution is going to be take your analytic data and store it somewhere else, and your transactional data and keep it here. That's your long-term solution. It's not that easy to do, but that is your long-term solution when you get to that point where like you have non-clusters everywhere. That's your kind of solution. Yes?
Can you expand this a little bit on why a vacuum does not improve query performance?
Great question. So vacuum in Delta Lake, its purpose primarily is to get rid of old data and apply retention. So let's say I have nothing automatic in place. I have 1 year retention, and I do nothing. When I hit vacuum, it's going to remove any data older than a year, any transaction log information older than a year. And so that won't make queries faster, because queries grabbing the data from any point in time are going to go in that point in time and grab the data. If that point in time is outside of your retention period, it's not going to get you anything at all. But if you're going for current data, you're going for your current checkpoint. And so nothing changes. If I want current data, I still go to my current checkpoint. If I want data from 2 weeks ago, I still go back 2 weeks in the history to time travel. But getting rid of data more than a year ago won't impact the performance of that. You'll reduce your storage size, and you'll enforce your retention period, but it won't fundamentally improve the performance of any queries unless that query happened to go to data that was more than a year ago, in which case now it'll just return nothing because you don't have the history anymore. And so the question really was like, what happens when, why doesn't vacuum impact performance? And that's kind of why, is that it's only getting rid of old retention-related transaction log information. It's not removing data and shrinking your data.
Not just transaction log, it removes the files that have been updated within versions of them.
Correct? Yes. Right. It's not. I mean, your performance on queries will not improve because your queries are hitting the same files no matter what. But as old files go away, your storage footprint goes down, and you have less data. There's always technically there's less metadata to interrogate, but that's fundamentally like trivial, I think. So it's just not an optimization. It's really just meant to enforce retention. It won't make queries go much faster, but it will reduce your storage footprint, which is always nice. I hope I'm explaining that well. If I'm not explaining, we can chat later if I'm explaining it poorly, and I apologize. That's kind of how I see it. Are there any other questions here about anything related to analytic data storage, as we're hitting the end of our time, and it's been a long time? Anybody have anything else? One more hand. Yes?
Since all the data is stored in Parquet files, is there anything in the DMV that we can see?
Oh, so if you're storing data in Parquet, it'll depend on your implementation, ultimately. So it really will, whether you're in Fabric or in Databricks, they have their own window into the data, and you have to use them to see it. You can very easily go in with Python or whatever and query and look at the files and understand how they're stored. But most modern implementations like Fabric will provide insight into metadata. It's not through DMVs. But you can look at it, through the GUI or through a command line. I've always found that like the Columnstore indexed metadata was an easier solution because it was more built in early on. But you can, if you want to view it. Like all those files are there, and you can look at them. Nothing stops you from looking at them. They're there. The JSON files are just JSON files. You can open them and look at them. Parquet files, you can't really look at them naturally. You have to load them into something that will help you view them. But in general, I wouldn't be looking at metadata unless I had a problem. That's really something you do when you have a problem and you want to try to solve it. Then you go in and dig in and try to understand why are things not working the way I want them to work. But I would never dive into metadata unless I had to. As curious a person as I am, I don't want to go digging in nitty-gritty details until I have to, because it's a lot of work, it's a lot of time, it's a lot of effort. It's just kind of a piece of guidance, I guess. All right. Well, I hope you appreciated and enjoyed this. This is part of a learning pathway today. There were separate sessions earlier on Columnstore and on Delta Lake, and now we've made it. A total of 5 hours of content related to analytic data storage. I hope you enjoyed this, and I hope I didn't put you to sleep. I don't see anybody sleeping right now or snoring, which is awesome. 2.5 hours is a lot of content. So thank you very much for coming today, and feel free to chat later if you want to talk about any of this more, and we can chat.